Hello.
Good morning.
How
How are you?
Fine. Can you hear me now, Adam?
Yes, sir.
Very good. I hear you loud and clear too. Very good. So thanks for sending the recorded presentation.
Oh,
yesterday.
no problem.
We'll collect them all and decide what we're going to do. See, we need to have, let's see who we have now.
Hello, Professor.
Hi.
Oh, I'm the student assistant.
Hi, Linan.
Hi, how are you?
Thanks for helping. Yeah,
No problem.
Fine. Thank you. We need, is Daigo on? On? No. We need Alex, Gang, and Daigo. And I don't see any of the speakers yet. Okay.
Right. We do have Sergey Oliver, or there's two names. I'm not sure which one's which, but he was on the list.
Who?
Or it's Simonge Kamguya.
Who is here? I don't know.
He was on the list today.
No, I don't have it on the list.
Sergey Oliver, yeah.
Maybe later in the 12 to 4 session. Yes.
Right,
Yeah.
right. 12 to 4. Yep.
Yeah. Right. Right in the morning, I need the Daigo Shishika from George Mason, Alex Sprintson from NSF,
Right.
Gang Chu from NSF, and I don't see any from University of Maryland.
Right. They're not here yet.
No. Should we send?
I went ahead and promote. I promote anybody on the list as soon as they arrive. So
Yeah, no, that's fine. That's fine. That's
okay.
fine. Yeah, yeah. Because I mean, we will not have a break. You see, we'll go. If you look at the program, after 12, we'll go immediately on the other one.
Okay.
This time around, we didn't have the luxury of having a few minutes, but I mean, we will create a couple, but that's about it.
Right. So if I have to step away again, should I just chat with you like I did last time?
Yeah. That's fine. We have.
Shouldn't, it should be, if I do, it should only be for a minute or two.
That's fine. We have Linan and myself, and we're fine. Okay. I'm just worried about should I send an email to people because they have to log in.
And I've made him co-host as well, so
yeah,
he should be able to do anything.
Yeah.
If I have to step away. Okay, great.
Let me see if I need to send an email to people. Yeah, I'll try to do that. Let's see. Because it's 10:20 almost. And I told everybody to be on
10:15, I believe.
Yeah, that 15 minutes ahead of the.
Mm-hmm.
But I don't like teleworking. You can't control anything. It's just you have to rely on the self-control on people, and that has great variability. Trust me, my friend.
Yeah, I believe that.
Yeah, okay. It's interesting.
I'm only semi-disciplined.
No, I didn't mean anything for you. I just mean.
No, I know.
In general, it's just.
No, I understand. I'm just kidding around.
Yeah. Let's see if I can find a way to send them an email. Yeah, here we are. I just send them an email. See what happens.
Are most of these in the same time zone? I don't have the full list in front of me.
Yeah, they're they're actually in the area. The one is from George Mason University, the other is from NSF, and the other is from UMD. Okay.
So then, yeah.
No reason, no justification.
Yeah,
trust
right.
me. Trust me.
Yep.
I know what I'm doing.
Gotcha.
But yeah. Maybe I should send them the link.
Hello.
Hello, how you doing?
Oh, hi, Daigo. I was just sending you another email to tell you where to click. But I'm glad you're on. Thank you. You're the first presenter, okay?
Yes. Hello. Good morning.
Hi, good morning. What department are you in George Mason?
I joined the mechanical engineering department. It's very small currently, and we're.
I know.
Yeah.
Yeah. It didn't exist 5 years ago almost, right? I know George Mason very well, yeah.
Okay, great. I worked with Derek Paley at UMD, so. So after that, I joined Vijay's group as a postdoc. So I've seen.
Oh, so you are a UMD graduate?
Yes.
When did you graduate?
2017.
Okay, all right. Okay.
Yes.
Yeah, okay, good.
So yeah, we never talked, but I've always seen you in different seminars for ISR.
No problem, that's okay. Yeah. I've been in the 2 committees of current students of Derek.
Oh, nice.
2 PhD students, yeah.
Great. I also work with Dipankar Methi these days.
My student, yeah, right. He's at the University of North Carolina, Charlotte. Just joined, like you did.
Yes.
Yeah. How do you know Dipankar?
So the thesis program that Vijay is leading, we meet there.
Oh, yeah, right. Yeah, right. Yeah.
So actually with the ARL folks, we work on these pursuit evasion game type of problem.
Yeah, right. So did Dipankar get some funding from that program? Hi, Alex. Good morning. I cannot hear you.
Yeah, sorry, I was muted. Hi. Sorry.
No problem. Bye. Good morning. Yeah.
Good morning.
So the last one we're missing is Gang, but at least we can start. Yeah. All right. We have the first 2.
I think we're not starting until it's 10:30, right?
10:30. Yes. 10:30, and we will not have any breaks. Okay. So the deal is you each speak for about 25 minutes. We have half an hour, but including questions, and I need to keep the time tight. So if you try to finish it within 25 minutes, then we can have 5 minutes of questions, which would be nice. Yeah.
I should be able to share my screen, right? So can I just test it? Okay, so just...
Yeah, every panelist can do that.
Okay, so I'll just share screen.
Yeah, including Lina and myself, yeah. You see, in this webinar thing, you have two categories of participants, panelists and attendees, okay? And we're all panelists. Okay. Yeah, we can see your screen, yeah.
Can you see, which screen you see? You see presenter screen or you see kind of...
we see both.
Oh, you see both, okay.
You can select the area that you want to show.
Okay, let me just stop sharing. It's okay, I will figure it out. Okay, so just a second. Oh, I think if I do now, like, can you see only presenter screen or you see?
Yes, no, that's fine. Just this is just fine, I think.
Okay.
Just the slides, right?
Just the slides. You don't see my internal screen. Okay.
No, that's fine.
Okay, great.
So now what you do? Where are you originally from?
Originally Russia, but I got educated in Israel. So it's
yeah, because your accent is Russian, and when I saw your name, I said it doesn't sound like Sasha, of course, yes, but I mean the other.
Right.
Okay, all right. But when we were talking the other day on the colloquium that I was participating, I got the first time to listen to your accent. And I said this fellow is from Russia, 100%. So
we figure it out.
Huh?
You figure it out, right?
No, I have lots of friends in Russia, trust me. Many years, since the 70s, actually. Although I haven't been there now for about, 5 years.
So how many participants are roughly in this conference?
I guess there are 265 registrants.
Okay.
Yesterday we had anywhere from 45 to went all the way to 70 sometimes.
Okay.
During the sessions. It's like conferences, like people vary.
Yeah.
From sessions. And this one actually, you can get out in and out easily.
Sure. Yeah, my presentation is a little bit higher level, so hopefully it will be okay. But also, like, it might not be as related to game theory, but I will try to.
But that's the whole point. The reason of having these invited talks is to actually try to increase the number of topics that people in this audience are working on, okay? And also increase what we mean by security, not just security communication network, but also security and protection in areas. Hi, gang. Welcome.
Hello.
Hi, how are you?
Good.
Did you have your morning coffee yet?
I never drink coffee, but I'm awake now.
What do you drink in China to wake up in the morning?
Nothing.
Oh, come on. I mean, I've been there. You drink some strong stuff. Come on.
Ice cold water.
Yeah, that's good.
So 0 degree water.
Sometimes the coffee I had in China was not very good. I could feel the particles, all right? Because they make it with the steering and all that stuff, okay, in some of the universities. But in some of the better universities, you can find all this stuff we have here as well. First time I went to China, it was in 81. I have to show you pictures to see how the universities that you know now, how they were at this point. Let me just say that Chengdu was just a village, and you can compare what it is today. It's a city larger than New York, right? It's amazing. I have a picture from the Chengdu Institute of Technology where I gave a course on inner filtering in 87. Yeah. Very interesting what can happen in 30 years. Okay, 1 more minute and we'll start. Hello, good morning to everybody. My name is John Barras. I am the General Chair with Radha Puvendran of GAMESEC 2020. And today I will chair this special session with 3 very interesting invited papers and presentations. The purpose of these invited presentations that we introduced this year is to give to the audience of GameSec some new ideas and new areas where they can actually try to apply game theory and also try to get a broader view of security, trust, and privacy. So the first presentation is by Daigo Shishika from George Mason University, with title A Review of Multi-Agent Perimeter Defense Games. Daigo, you're on.
Thank you. I'll share my screen. And hopefully you see my main presentation. Okay. Well, first of all, thank you very much for inviting us to this session. It's a real pleasure. And my name is Daigo Shishika. I recently started at George Mason University. But prior to that, I worked with Vijay Kumar and collaborators at University of Pennsylvania. And the work I'm presenting today was done at Penn during my years of postdoc there. I'd like to begin by a little bit of context on where I come from. So in my research, I studied effective coordination and cooperation for multi-agent systems. And the premise I have is that a competition against adversary induces effective team behaviors, as we see in many different sports, as well as natural system like Starling block competing against its predator. And when we say adversary, it could mean many different things like cyber physical attacks, or more generally uncertainties or internal failure. But what we look at in this work is security against autonomous adversarial swarms. So it could be a sort of a classical example of game theory in a sense that it's related to pursuit evasion game, originally proposed by in a seminal work by Isaacs. But what we look at here is given a target, high value target that the defenders want to protect. And there's intruders that try to intercept or enter this target region. So we could think of this as a building that the defenders are protecting, or it could be of larger scale. For example, deploying a group of robots around airport so that any intruder or any vehicle that tries to enter the region will be detected by the camera mounted on the robot, for example. And to formulate this as a game, we assume that intruders score by reaching a target, and that the defenders try to minimize this score by capturing them. And as an example shown in this video, I assume that the defenders move along the perimeter, and we denote the final number of intrusion by this big Q, which is a function of initial configuration and defender and intruder strategy, team strategies. And here, strategy is a mapping from the states, which is the positions of all the agents, to the actions, which is the velocity vector of the agents. And we're interested in finding the equilibrium team strategies and figuring out the outcome of the game, which is the final number of intrusion that occur. And we make a couple of assumptions, which I'm interested in removing or relaxing in the future. The first one is that defenders move on the perimeter, as you see in the video. And the agents have first order dynamics, so they can change the velocity vector instantaneously. And everyone knows where everyone else is, so full state information. And capture is defined by zero distance or collision. And we assume that the attackers are at most as fast as the defenders, but never faster than the defender. So as related work, this was a target guarding problem. The 1v1 version was originally proposed by Isaacs. And so the version or variants of this problem has been studied under the name target attacker defender game, or reach avoid game, where there's a lot of publications from Claire Tomlin's group And application has been considered in missile guidance and navigation, or border security, coastline guarding. Those applications where Eloy Garcia et al. From AFRL have a big group of work there. And when it comes to swarm versus swarm, or many player setting, the high dimensionality of the state space makes this problem very hard to solve with conventional approaches. And one pioneering work done by Chen et al. Approximated this into a combination of one versus one problems and reduced the design problem into assignment problem. So this was a very useful approach in reducing the complexity. And what we're interested in here is thinking about teaming behavior, whether we can have more sophisticated or complex teaming behavior beyond just man-on-man assignment, and think about whether we can actually improve the performance of the defender team while maintaining computational tractability of the algorithms. So common approach in these problems is to start with agent level feedback law by looking at these microscopic games, 1 versus 1, 2 versus 1, using game theory. And then think about team level strategy, addressing who should pursue whom. And in this presentation today, I will review 3 different approaches: maximum matching, MM, maximum independent set, MIS, and LGR is something we propose in terms of decomposing the game using local game regions, LGR. So with that, I'll start with briefly reviewing the 1 versus 1 game. So given a circular perimeter and 1 defender, 1 attacker, we can nicely use this polar coordinate to define the states of the engagement and write down the dynamics and define the terminal condition of the game to be the time when the attacker reaches the perimeter, and define a zero-sum game where the payoff is this target intercept distance. Basically, the attacker wants to maximize the distance when it reaches the perimeter, whereas the defender wants to minimize this distance. And we can solve for equilibrium strategies. And in the end, we get a very simple strategy. For defender, it wants to divide the space into left side and right side and move towards the side that the attacker is in. Now for the attacker, it considers the circle scaled by the speed ratio nu and goes for the tangent point on this circle. So you can imagine if the speed ratio, if the attacker's speed goes to very slow as compared to defender, meaning speed ratio nu approaching 0, then the attacker will try to go directly towards the closest point on the perimeter. Whereas if the speed ratio approaches 1, the breach point is going to be the tangent of the perimeter. With this strategies, we can find the value of the game in closed form here. But we can also extend this to non-circular parameters. In this case, the left region and right region is going to be slightly more complex than circular case. And there's no polar coordinates anymore. So the attacker strategy is going to be parameterized with this approach angle phi. But again, we can find the equilibrium approach angle to be a function of this parameter speed ratio nu. And we see again that if speed ratio goes close to 0, it's approaching, it represents approaching the closest point on the perimeter, whereas nu approaching 1, it's the tangent point on the perimeter. So this value of the game, it has to be computed numerically in this case, but we obtain something that looks like this in this picture. So this is showing a level set of the value function for a specific defender position. Given an intruder position in the 2D space, it immediately tells us what the final intercept distance is going to be. And as you see in this animation, If both agents use equilibrium strategy, then they're going to stay on the level set of this value function. And moving forward, what we are going to use is the result of the game of kind, which tells us which agent can win. And the winning region is going to be useful in looking at that. So this red region is showing where the value function v is positive. If the attacker starts inside, it is guaranteed to win no matter what the defender does. But if it starts outside, then the defender has a strategy to keep the attacker outside of this winning region. And so the attacker cannot penetrate the perimeter without being captured. So this pairwise result immediately gives us a naive teaming behavior, which is the first one, maximum matching defense strategy. So given multiple defenders and multiple attackers, we can use this winning region to figure out which attacker can be captured by which defender. And then we can encode this information into bipartite graph. And by solving maximum cardinality matching, we can optimize the number of capture guaranteed by the defender team. For example, this. And this animation is going to demonstrate this maximum matching strategy where this attacker on the right-hand side, this guy is in the attacker winning region against every single defender. So no defender can guarantee capture of this single attacker. As we expect, it makes it to the perimeter. So this is a very simple coordination strategy that makes sense, but it does not have any optimality guarantee. And what's missing here is the cooperation among the defenders, which we can see from 2 versus 1 game. So this is a scenario demonstrating 2v1, 2 versus 1 game. From this configuration, the 1v1 analysis tells us that no defender can guarantee capture. Basically, the attacker can move towards the left to win against the blue one, and it can move towards the right to win against the orange one. However, if the two defenders cooperate and perform pincer movement, they can actually team up to expand the defender's winning region or reduce attacker's winning region, which is specified by this highlighted in this yellow. So from this configuration, actually, the defender pair are able to capture this attacker. And from this additional result, we can slightly improve the maximum matching strategy. Here, looking at additional 2v1 defense, we can augment the bipartite graph using nodes representing pairs of defenders. However, we cannot immediately apply a maximum matching strategy because there could be potential conflict between paired defense and individual defense. So what we can do to avoid this conflict is by labeling the assignments, generating a new graph, and then solving maximum independent set problem in this new graph. For example, 4 and 5 or 5 and 6 have no overlapping defender or attacker, so they're valid assignments. The problem with this is, first of all, MIS is computationally expensive, and secondly, these solutions are non-unique, and we cannot tell which assignment leads to better outcome. So still no strong results on optimality here. So we invented sort of a new way to decompose the game using what we call local game regions. The basic idea is from the winning region generated in 2 versus 1 game. Here, the attacker starting inside of this red region, it can reach the perimeter, and we call this local game region. And if we have multiple defenders and attackers, we can construct multiple of these regions based on different pairs of defenders. And for every single defender, local game region, we can define subteams of defender as well as subteam of attackers. And what we care about is the number of agents in these teams. We define this quantity Q, which we call local game score, and this denotes the numerical advantage of the attacker team in each of these regions. And the significance of this number is that the attacker team can actually guarantee to score if they leverage this numerical advantage and approach the midpoint between the two defender that is constructing the boundary. And now with this small result or local result, we can construct the global intruder team strategy. So the way we think about this is we can think about attacker teaming based on or induced by these local game regions. By picking disjoint set of regions, we can compute local game score in each region and consider how we can maximize the summation over all these regions. And in this case, we have one subteam guaranteeing score of 2, another subteam guaranteeing score of 1, and in the end, the overall score is 3. So this attacker team strategy guarantees a lower bound on what the attackers can do in this game. And importantly, this optimization is polynomial time with respect to the number of defenders. So I'd like to note that this was the first as compared to maximum matching or maximum independence set, where we could induce this sort of attacker strategy, not just defender strategy. And now we can also use this decomposition method to design defense strategy as well. The idea is that the defenders want to make sure that the attackers don't increase their numerical advantages. So whenever the attacker is approaching a region with Q equals 0, meaning it's already occupied, there's already the same number of attackers and the defender in the region, the defender can perform pincer movement to avoid any additional attacker entering this region. And with this method, we can identify possible 2v1 defense, and we can assign 1v1 to the rest. And basically, this is the algorithm of assigning defenders to attackers. And this animation demonstrates what happens. And the theoretical guarantee we derived in the original paper was that defender team can capture all intruders if QLG equals 0. I'm not going to talk about the proof of this, but what's really interesting is what the algorithm does. If you can focus on the yellow defender, it cooperates with purple one first until the attacker here is guaranteed to be captured by purple one alone. And then once that is guaranteed, now yellow turns to cooperate with the orange one to guarantee capture of the next one. And now when it's taken care of by the orange one, yellow moves on to 1v1 defense. So this was the only sequence all of the intruders could possibly be captured from this initial configuration. But importantly, the algorithm we came up with comes up with this assignment method without any explicit prediction into the future. And now recalling that this is only for QLG equals 0 case, what happens when QLG is positive? In other words, when attackers can actually score. What we do in step 0 of the algorithm is remove QLG uncapturable intruders, identify those intruders that we want to remove from the game, and play the virtual game where QLG equals 0, and guarantee capture of all the remaining attackers in the game. So with these two lemmas, we have this result saying that defender strategy that we just talked about bounds the score from above by this quantity QLG. And combined with the previous results from the attacker's side, that the score is guaranteed to be greater than or equal to QLG, we have this inequality showing that these two defender and attacker team strategies are at an equilibrium. And the final outcome of the game, the number of intrusion, we can estimate from this optimization problem. So this is very useful in designing defense systems, because if we construct a perimeter, find a number of allocate defenders and consider possible locations of the intruders, we can immediately estimate from this optimization how many intrusion can possibly occur. If this QLG is 0, then we can say that no intruder will be able to penetrate. So this is just an example showing the case from this initial configuration. We see that QLG equals 0. Sorry, QLG is 2. And in the end, 2 intrusion occurs. And this is a comparative study demonstrating the effectiveness of the local game region-based strategy. So the left one, we have maximum matching-based approach, allowing 1 intruder to penetrate. Whereas the local game region-based strategy, we have 2v1 defense happening at the beginning, and then dynamically changing the assignment, all of the intruders are going to be captured. So with this, I'd like to summarize the 3 team strategies I presented. So first one is the maximum matching. It was based on pairwise results. So it's computationally efficient and it's easy to extend. For example, when the agents have different speeds, we can just apply this method as long as we know what the speed is, capability is. And for attacker weights, things like that, we can also accommodate. However, it was suboptimal and no intruder policy was considered. The MIS approach slightly improved on this by considering cooperative defense, but it was computationally inefficient. The LGR, it was based on 2v1 results, but using this region, we could accommodate a more generic number of agents depending on the subteam size. And importantly, this provided intruder team strategy. However, since this is well tuned for this specific perimeter defense game, it's harder to be extended to other problems. So I'd like to spend a little bit of time talking about the limitations of this work and future directions. So the first limitation is obviously the defender dynamics that we assume defender to stay on the perimeter. The implication is that the defender can only capture 1 intruder because the intruder can basically consume 1 defender by staying in front of it. As soon as defender moves, then the intruder can make a score. And for the defender to avoid that, it just has to stay there. To avoid this degeneracy, we can think about defender freely moving in the space, but then now there's a question of sequences of capture that occur. For example, there's 1 defender versus 2 attacker scenario studied by Garcia et al. And also for translating targets, Smith et al. And a group of work from Francesco Bullo's group, they consider vehicle routing type aspect of these intercept problems. The challenge is when we have multiple swarm versus swarm scenario, multiple defenders, when we have to do assignment and routing on top of that against evasive targets, this will be realistic, but very challenging in terms of computation. And information and payoff structure, what if we have limited sensor footprint? So in our related work, we considered patroller and defender type of task decomposition where controllers guarantee the detection of incoming attackers. And there was also work on decentralization of centralized policy using learning technique by Jimmy Paulos at UPenn. However, we couldn't really think of any explicit type of searching behavior. So it'll be interesting to see how this partial information induces more sort of richer set of behaviors like search, deception. And information could include other things such as parameters of the game or opponent's motive, which leads us to thinking about more realistic payoff function rather than just scoring based on breaching. Maybe it can incentivize evasive behavior, or maybe we can model reconnaissance or scouting type behavior by manipulating our payoff function. So as a conclusion, we looked at perimeter defense game, 1v1, 2v1, and how we can look at team strategies from different perspectives, and talked about how dynamics, information structure, and payoff structure can be improved in future extensions. So with that, I'd like to thank my sponsor, ARL Grant DSIST, for funding this project, and thank my collaborators at Penn, FRL, and UNC-ARL, and take any questions. And one last thing, I'm looking for students. So if you know anyone interested in this kind of project, please connect me. Thank you very much.
Thank you, Daigo. Any questions that you may have? There is one question in, okay.
May I start? Oh,
yeah.
Thanks for the presentation. It's a really interesting topic. So I guess now we assume like all the players has complete information that they know the location exactly. So I'm curious, like if the defender, for example, his observation of the intruder's location is noisy, and the intruder actually know that, how this imperfect information will affect this region of capture? Like it's become bigger or smaller?
Yeah, that's a great question. So I think, there are many ways we can think of that sort of uncertainties. The one you mentioned, I think if the region, for example, this kind of boundary, it's purely based on the defender location and the speed ratio of the agents. So if there's uncertainty in the agent speed, then this boundary is going to be blurred, sort of. If the uncertainty is the sort of source of uncertainty is in the position, then now I think it comes down to how likely, if we have a distribution of the positions, how likely it is contained in the winning region versus outside of the winning region. So it's kind of an area integral over that distribution.
Okay.
So,
is there like related work on these topics? I think you mentioned the like limited information, but you mentioned it's like
so no, currently no. So it'll be a good future direction to consider uncertainties in either positions or parameters.
Yeah, I have one question along the same lines. I mean, I want to make it clear that everybody knows everything here, right? The information, everything is known a priori to everybody.
Yes. Okay,
so in realistic situations, that won't be the case.
Yes.
So, and even if it is, even in that case, the more specific question I have is, why isn't it possible for the defenders to do randomized defense, even when everybody knows the information, and actually do better? Because if I start moving around randomly, you will not know where I am. So if you're the attacker, you have a problem. Which way to go? So even this simple randomization may actually be interesting to as a next step. What do you think?
Yeah, randomized or mixed strategy. That'll be also something interesting to think about in connection to partial information, because everything here is both full information and deterministic. So that.
Yeah. Okay. All right. We can continue the discussion, but we have to go to the next talk. Thank you very much, Daigo, for a very interesting talk. Okay, so the next presentation is by Alex Sprintson, who is from Texas A&M University, and now he's at the National Science Foundation. And he will talk about the taxonomy of security and privacy requirements for next generation wireless networks. So Alex, you have the floor.
Yeah, thank you so much for inviting me. I just kind of wanted to confirm that you can see my screen, right?
Yes.
Okay, thank you so much. Yeah, thank you so much, Professor Barras, for inviting me to talk. So as mentioned, I will present pretty high-level overview on securing next generation wireless networks. We'll talk a little bit also about privacy. Yeah, so just a disclaimer that whatever is presented here is just my own opinion, is not necessarily represent the view of NSF. I'm more with my academic hat here. And what I will try to do is just trying to kind of present views of what is missing in research, what are opportunities, what are challenges for securing next generation networks. And as a result of those challenges, is definitely a lot of opportunities for research community to work on them. So in general, if you look on 5G generation and beyond mobile broadband networks, they definitely very promising technologies, right? There's a lot of potential benefits for all people in affordable broadband, as well as enabling new types of applications, for example, low latency communication. And also we can, for example, build applications taking advantage of position accuracy, so we know where devices are, be able to communicate with them with high bandwidth and with low delay. And it's definitely just kind of a plug for NSF. So many of those technologies are built on NSF-funded research. For example, research on spectrum sharing, using millimeter wave frequency bands, and software-defined networks. Blocks for next generation networks. So first of all, it's more efficient use of electromagnetic spectrums. We can use from 600 megahertz to potentially 100 gigahertz in the future. If you're looking on 6G and beyond, people talking about terahertz. So definitely we'll get more spectrum, but it's requires us to build better electronics to take advantage of those high frequency bands. Also spectrum sharing, right? Because mid-band spectrum is limited, and building better channel models. So we also need to have a better spectrum efficiency. So for example, using spectrum signal processing techniques and interference cancellations. Also what we see in 5G, 6G and beyond is a switching from very hardware heavy technologies to more software defined networks. So many of the functions can be implemented in software, and definitely we'll see use of cloud and edge cloud to implementing those functions. We also see many novel uses of wireless technologies, not beyond communication. For example, people talk about spectrum sensing, even power transfer. So next generation networks, they have those take advantage of those novel uses. And definitely when we're talking about next generation networks, it's hard not to talk about AI, and this will have internal implications for security as well. So AI and ML will be one of the major enablers of such technologies. So we'll use those AI technologies for anomaly detection, for prediction, for recommendation systems, and detection and classification. So we'll definitely use them for many of the security functions. But by using AI and ML, we also potentially expose ourselves for different types of attacks. Then attackers can take advantage of us using those technologies to attack the network. So again, if you're looking on those 5G and beyond technologies, it's really a game changer. Because when we typically think about wireless and cellular networks, we kind of think about consumer devices, smartphones, and enabling communication between users and access to web and stuff like this and all kind of applications. So why 5G and beyond becomes a game changer? Because we now connecting a large number of IoT devices, Internet of Things devices. And also we have a lot of, so this will require machine-to-machine communication. So basically all those next generation networks, they becoming a player in many, many new areas and industries. And we see that different providers such as DoD and others, instead of building their own networks, for example, for logistics, they will rely on 5G for communication and control. So for example, if you look on smart grid providers or power systems, they need definitely communication for all this advanced SCADA networks or synchrophasers. They will definitely use 5G networks instead of building their own infrastructure, if 5G will satisfy this promise of security and low latency and high bandwidth. Other kind of electronic health, we'll see a lot of uses in transportation system with autonomous drivers and collision prevention, and controlling physical infrastructure, civil infrastructure such as water. So this is why it's a game changer, because we have this transition from traditional usage to more machine-to-machine and IoT use. So, and generally, if you're looking on threat taxonomy, such a huge network that connecting billions of devices located across vast geographical areas is definitely susceptible to attacks. And we can definitely see that it can be attacked from many angles, right? And this is, in this picture, we'll see just traditional networks, but in 5G, it will be more prominent of a way of attacking such networks. So we can start with user devices, right? So definitely such networks will connect a large number of IoT devices, and those devices will be unprotected in many cases. Then we have this radio access network, and definitely a lot of communication will be through physical layer, and physical layer is a shared medium that everybody can potentially attack, right? And we'll think about denial of service attacks and interference, jamming. So we need to find some ways to mitigate this. And kind of another interfaces between radio access network and core network, definitely we can think of attackers doing some kind of staging, manage the middle attacks and others. And in addition, in core network is a complicated network that uses slicing and other techniques, and also can be shared by multiple providers. We can think about attacks there. All of this will be using hardware that comes from different sources, which also potentially introduces attack vectors and kind of can attack surfaces and many others, right? So those networks will use cloud. So for example, will be cloud, many of the functions will be executed at cloud, which also opens ways to creating trouble for this network. So again, just to reiterate, is a game changer. We'll see that those networks will be have a lot of societal importance. We'll see also, for example, in the United States, the Congress recently passed this legislation of securing 5G. And this is just evidence why people are so concerned about reliability and security of such technologies. Right, and again, this transition from consumer to IoT, and also supporting a variety of verticals such as transportation, safety and defense, for example, first responder networks, and supporting other life critical applications. Also, this increasing bandwidth and low latency will create new applications such as AR, VR, and video analytics. So what is in 5G? Why it's 5G and beyond, right? So what are enabling technologies? And it's also important to understand, since we're talking about security, it's important to understand what is the system and what basic components of such systems. So first of all, it's built of massive MIMO technologies. It's one of transition from LTE to 5G. So we have multiple input, multiple output MIMO, but it's a massive antennas arrays that enabling this communication between user and IoT devices. Second is using of frequency bands, high frequency bands such as millimeter wave. Right, this will require techniques such as beamforming, which is also have implication on security. In some way, it's helping security because we can send energy in more directed way, and probably will have higher. Harder to jam, but on the other hand, it's more complicated and sophisticated system, and as we know, the more complexity is always have some implication on security as well. Next technology is virtualization and software-defined networking and disaggregating network functions, enabling software controls. In general, we can definitely use it for creating additional security functions, but also with network slicing, it can open door to additional attacks. We also see transition to microservices architecture, such as serverless computing. So we can basically create microservices, right? So kind of pieces of network functions that can focus on executing particular function. We also see use of edge cloud, right? So basically, radio access network will have some computational and storage capabilities, and also use of artificial intelligence on all levels of networks. So this will enable us transition from traditional networks for next generation. And it's important to kind of recognize this to think about security. So again, why it's a disruptor, right? So we transition to machine, new stakeholders and players, use of integration of multiple technologies. As I mentioned, for example, we can use cloud together with millimeter wave, together with massive MIMO, together with SDN, right? So how all of this integrates together and how to protect such a system, because it becomes more and more complexity. We also see increasing flexibility in system design. So no longer we can build our systems that we're using particular spectrum band. We have a spectrum sharing, or we can use multiple spectrum band, or we can share between, for example, next generation cellular and traditional Wi-Fi networks, right? So basically, some of the spectrum can be shared. And this is also kind of has implication on security, because all this flexibility make it harder to protect the system. Because what about players that might not follow the rules? And this is where game theory can definitely help. So if you're looking for future topic for research, this can be potential interesting topic. Also, we have many plug and play applications, right? So for example, in traditional, in transportation and others. So also it's important to realize that 5G and next G is not only about connectivity. We also have some control functions, for example, in smart grid. Because of low latency, such as networks can have some functionality to control some physical systems. We also, content becomes a first-class citizen, right? So we no longer want to connect to specific server, but we want to kind of get some information. So data-centric networking become more prominent, and those networks become also, will have a content distribution functionality in them. And in general, connectivity as well. So it's different types of network we're talking about. So unfortunately, in design of such network, current focus is on performance and functionalities, and missing focus is on security and robustness. So we're making the same mistake in developing such networks. We're first talking about what performance requirements, right? So how many gigabit per second those network need to support, and what functionalities they need to support. But security is afterthought, right? It was always the case, and unfortunately it remains the case. And this definitely introduces a problem, right? So as a traditional way of reasoning about security, let's first build the systems that satisfies those performance requirements and functionality, and then think about what are attack surfaces, right? How to attack the system and how the system can be hardened and secured against those attacks. But a much more promising way is to introduce security much earlier in the design process and think about security as a first-class requirement, not only performance, but robustness and security of such system are even more important than performance, as such systems will be having this life-serving functions. And definitely growing complexity of such system is a reason to concern, because a more complex system will be harder to protect. And definitely in a traditional way, we see short-term approach to patchwork security, right? So let's just see where the problem is and trying to patch it, but it will not provide guarantees for traditional behavior. So this is where research community can contribute by thinking about security in advance and introducing those security functions much earlier in design process. So for long-term goals for security and privacy as well, is to think about how to provide security end-to-end. So right now we can definitely have a good tools to thinking about security in different components alone. For example, people think about security on the cloud application, security in core network, security in radio access network, and security in physical layer. But all this, it's important, right? But much more important is to tell users that you have security end-to-end. So you have your slice of the network, which includes IoT devices and servers on the cloud and other functions and edge, right? How we can reason about this and make sure that provide some guarantees on security from end to end. And this will require composition of different security functions and those different components, and think about security composition. Another important thing is that different slices of the network might not be the same, right? So if you have a slice that serves consumers, it might not be as security in this slide might not be as important as slice that serves smart grid applications or defense applications or autonomous driving applications. So we can potentially provide tunable securities at different slices that have different security guarantees, and also we can have security as a service. So we have because in 5G, we can actually sell instance of the network to a provider, right? So for example, smart grid to utility company. And we can basically tune the security according to the need on this customer. We can also think about programmable security. So right now, security is more relying on static configuration. So we configure the network to be resilient against different types of attack. You can think about like firewall configuration, right? So we basically supplying this firewall with specific settings, but those settings are static. How we can transition from static to dynamic, because attackers are very smart and very agile and very evolving. So how we can, instead of configuring this security function, we can program them. So we can see that based on types of traffic that we can see or based on traffic attack, we can dynamically change the security posture in milliseconds instead of having intervention of human. And also, it's always be trade-off between security and efficiency. So definitely, if you want to have a highly hardened and secure network, we might not be able, with this heavy security, to be able to achieve the performance goals that we need for 5G. So we need to think about security functions which are very lightweight. In particular, if you have billions of IoT devices that by themselves are not secure. So how to have those light cryptographic protocols, for example, to because we cannot use heavily cryptographic and encryption functions. This is another interesting area of research, scalable security and lightweight security. Okay, so what are challenges, right? So if you just kind of go and see, we understand the system more or less, what are the challenges of securing such system? So the first definitely challenge of complexity, since we have such a system that takes advantage of those multiple technologies. If you want to allow flexibility and using different frequency bands, if you want to share a spectrum, right? All complexity of this is definitely contributes to challenge in terms of security. Also, we need to coordinate multiple levels of security with different levels, right? So we will have some security components in physical layer and cloud and edge network, how those different security functions are coordinated and how they interface each other. For example, in physical layer, we have a lot of information that could be used for security because we know signal strengths, we know the location of the users, but this information might not readily be available in other security functions that operates in cloud. So how we coordinate those multiple levels of abstractions and create interfaces to secure end-to-end, to provide end-to-end security. And also, traditionally, as I mentioned before, those security point solutions are prepared in silos for each particular component and might not work to distributed edge cloud systems that 5G and beyond will be using. So challenges, again, transition from static to dynamic. We also might need to leave that some of the elements might not be secure, right? It's not impossible to secure all those billions of IoT devices that will be used. Some of them might be compromised, and some of them might not be even possible to make them secure due to this requirements. Such devices should be simple and low cost. We also see that standards might introduce another problems in security, because standards are right now are written in natural language. They're written in a way that it's very hard to understand what they mean, right? They're very, very complicated by itself. They're not represented formally. And they might also include security backdoors, because standards are created by committee and different players might actually be interested in some of the parts of the standard being vague. So we definitely need to move towards presenting standards in more formal ways that we can reason about those standards and also verify real systems against those standards, which today is very, very hard. So another challenge is virtual environments. That definitely has a lot of advantages for example, creating different slices, but we need to understand security implications of this. And also security will not be provided in centralized manner, right? So it will not be one security function located somewhere. It will be decentralized, right? And how to do it as a decentralized applications, it's very, very challenging. So just kind of looking on different system components, if you look about physical layer, definitely such system will be susceptible for intentional jamming. It's definitely will be implication for example, for first responders that as they're trying to use Spectrum, but it can be contested by devices. And actually, those attacks are not hard to make, because attackers can take advantage of software-defined radios and some other components. So kind of as a result, there is a need to mitigate denial of spectrum access, for examples, and use of higher frequencies, because we have beamforming that potentially can help us. But all of this needs to be thought through and coordinated. And also, for example, spectrum forensics. So we need to understand what happened and why we cannot attend spectrum whenever we need it. So another challenge is, as I mentioned, hardware and supply chain security. So how we reason about trustworthy hardware design, and if we buying some components from different providers, how we know that it's formally verified, right? That this device can only do whatever it's designed to do. And software and SDN, right? Again, if you have more flexibility, it's make it much harder to test it. So for different slicing and virtualization, we need technique to separating slices from each other and eliminate attacks when slices created and resources allocated. And we definitely need to secure all different verticals, such as transportation, DoD, and so forth. As I mentioned before, IoT presents a unique challenge, right? So how we even secure billions of devices, our security techniques so far are limited maybe to millions, right? But how we switch from millions to billions, and how we secure such devices have so limited capability and power constraints and might not support complex functions. So with those challenges, we definitely have a lot of opportunities, right? So we definitely, as a research community, we need to think how to move to secure by design. When we're thinking about those protocols, how we thinking about security postures, instead of designing the system first and fully understanding the system and then applying security kind of considerations. How to compose security, right? So from all those small functions, how we can build a decentralized coherent operations. We also can think about clean slate approaches, right? So because of real 5G, 6G, we're always trying to support legacy applications. But what if we're not constrained, right? So how we would provide the security by design if we have flexibility to design any networks that we want. Definitely for AI and machine learning, as we know, even for traditional using of machine learning and image processing, it's easy to confuse this ML algorithms, especially if you not really have clear understanding how it works, right? Definitely we need to kind of, this can open door to attack, right? Because if you have some kind of black box that works amazingly, but it can be easily confused and taken advantage of by attackers. Definitely, we need to find a way to leverage formal methods such as theorem proving and model checking, but do it in a scalable way and practical ways that we can actually use it in practice. Another kind of opportunity is security metrics and indices, how we can say that one system is more secure than others, right? Using of more like probabilistic tools and say like what is the probability of that the system can come under attack. And also we need to realize that probably will not be able to achieve perfect security. So we need to kind of develop, and probably this community is a good opportunity, cybersecurity policies, right? So how we can have the cyber insurance market that people can think about what happens in terms of when the attack happens, right? So how we can compensate and provide insurance to all parties that are affected by this attack. Okay, so this is another kind of example types of research, right? So kind of developing cybersecurity policies for those losses from cyber attacks. And it's kind of definitely interesting research topic, right? For clean slate design, again, we can think avoid being boxed by existing solution and go beyond specific threat model, right? So how we can design a system that we can say that we eliminate a certain types of threats, right? And also for this clean slate, we can take advantage of data. As we can see, data is used for a lot of purposes for system design. It can be also used for security. And we might need to rethink different protocols, even session layer protocols to enable this. And the idea is to reduce those vulnerabilities by orders of magnitude. So then we can mitigate the rest with using cybersecurity policies. I will probably, due to a lack of time, I will just skip to kind of to tell a couple of things about privacy. So privacy is important as security. So this will serve a lot of sensitive users. So we need to minimize this leakage of privacy. And for example, and anonymity, right? So we use those traditional Tor networks in the internet, but those networks are outdated and antiquated right now, but can we do this in next generation networks that we can use this anonymity and in those virtualized environment with in the new types of networks. So how to enable anonymity and how to address censorship, right? So definitely those next generation networks will be much easier to censor than traditional internet, for which we have some mitigation, but we need to think that we don't want like different state factors to tell us which sites we can access and which sites we cannot access. So for this, since it's a new area, for example, from kind of my NSF head, it's interesting to develop research roadmaps. So to fully understand, so definitely this presentation was just scratching the surface and very high level. But we want to fully understand this new security challenges. Definitely developing testbed and cyber ranges that people can get some data and be able to experiment on such kind of network, right? And for example, all these traditional security providers, they can bring their equipment to this prototype of next generation network and see how it all works together. So we definitely need security data sets. It's kind of big problem, right? That we can, that our enable researchers to experiment and contribute to this, right? So right now, unfortunately, with NextG, only big players have enough resources to have those test beds and access to data, and also to understand those standards and understand the designs of our system. So the main goal is to lower barrier to entry, right? So we want researchers in different institutions that might not have as much resources to be able to contribute to this, but also to startups and small research groups. So having said this, thank you so much again for inviting me, and we have a few minutes for questions. I will be happy to answer them.
Thank you, Alex, very much. We have a few minutes indeed for one or two questions. Does anybody have any questions? If you can put it on the chat. I have a question that has been burning me for many years. Okay, I have several which you can read, but the most important one is that in these complex systems, we need to divide and conquer. you cannot do security all at once. And as you know, composable security is still a very open problem, even for small systems. So to what extent all these technologies, meaning the physical layer, the software-defined networks, the network function virtualization, and the heterogeneity of the network actually can help us in developing something along the lines of composable security. And in this context, is game theory across different layers and different resolutions and different agents maybe a helpful methodology for that? What do you think? What's your view from NSF on that problem?
Yeah, again, I cannot really speak for NSF, but definitely we are aware of the situation, and it's for us, right? So it's a very, very complicated system, as you mentioned, right? Even in smaller system is not well understood, right? So this is why we turning it back to research community to help us with that, right? But I think it's for example, yeah, we see that software-defined principles are actually helping managing complexity. Yeah. Right, so we definitely can apply the same to security, right? So we can create some interfaces and coordinate like through them like different security functions, right?
We already have seen applications of game theory to management of slices,
right?
Because you can have slices with different characteristics, different security, and there is a game. Actually, can be both competitive and cooperative game in this management. Okay, this has come up to various discussions we have with companies on managing slices. Slices, for everybody, so that you understand, is basically sub-networks that are defined just by software, and this allows you a lot of flexibility because you can do it dynamically, almost real time, quite often.
Yeah, those different slices, they definitely compete for resources, right? And also might be different providers involved, right? So providing those resources. But game theory is kind of think also for spectrum access, right? So it's definitely how to share a spectrum between different.
One important part of the slicing actually is the management of the access, which is the spectrum. And again, because there's competition or if you like cooperation, you can apply game theory.
Right, but kind of going back to you, if I can just 10 seconds, right? So it's kind of slice includes some physical layer component, right? So like spectrum and then cloud, right? It might have some resources on cloud, and cloud can be provided by completely different providers such as Microsoft or whatever, Amazon, right? So how you basically price this, right? Some core network and radio access network, right?
Well, in this latter question, the only comment I'll make is that the techniques that we have used for that problem is actually coalition formation, which is a form of cooperative games.
Right.
So you actually, it's a very interesting topic, everything you described, because I can see a mixture of cooperative and non-cooperative games play a role in all these problems, right? Anyway, let's move on. Thank you again very much. It was very informative. And let's move to the next presentation, which is going to be by Gang Chu from the University of Maryland. And it's actually related to what Alex discussed because he's going to talk about hardware security and trust, a new battlefield of information. Gang, you have the floor.
Thank you very much, John, and good morning, everyone.
We can see the slides. You're fine.
You can see the slides, right?
Yes, we're fine.
Okay. So first, thank you very much for John for the invitation and also, the introduction. And John has been, I've been in this department with John for more than 20 years, where John has been, 50 years or so. So it is a really nice thing to come to this society and then to present some of the works. And John has asked me to show the people what basic hardware security are, what the people in this area were working about. And I suspect that most of the audience were not exactly on hardware security. So my goal here for this talk is, in some sense, will be an introductory talk. And I'll try my best to answer the following three questions. So first, what is the role of hardware plays in security? And second, what are the key problems and the challenges for hardware security and the trust? And the last one, so how do we view hardware security and the trust from the perspective of information and game theory? So I tried my best, and I'm never a game theory person. So let's try to learn things together. Okay. So first, let's try to go through a very short history of the story of this long history about security. So this I mean, probably everyone knows this guy. And when we talk about sensor in this context, we are talking about his cipher, where basically we know that it shifted the letters by 3 positions. So people who does not know this information will not be able to reveal the secret or reveal the information. And then around the same time, there is a general in China, before the Han Dynasty, and his name is Han Xin. And this picture shows that how he counts his armies. So he's not going to count them one by one, so that also his enemies knows how many troops he has. So he's going to ask the soldiers to count 1, 2, 3, 1, 2, 3 in a sequence. So basically tell him at the end what is the remainder. And then count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 5 at the count, and then at the end, the remainder. And then finally count 7 as a group, and then report the remainder at the end. So that is why you see 3 people in a row, 5 in a row, and 7 in a group. And this is eventually, it becomes a very famous Chinese remainder theory. And eventually, let's fast forward to this World War II, and then this is probably people know, this is the Cypher Engine where the Germans they used, and it is called Anchorable. So what is the computation behind this? As I have mentioned earlier, so behind the sensor cipher, it is just a shift with simple addition or subtraction. And then behind the Han Xin's counting mechanism, that is the Chinese remainder theory. And then for people to break or to compute this in anger, so for this machine to be broken, that is the 3, polished mathematicians, they broke the system. But to really practically break the system, that in some sense motivates one great invention for probably the century. That is the things we call the computer. So these things, this abacus, this computer, these are the things which we call hardware behind this security, behind this computation. And so what is in general, what are the roles in hardware in nowadays, cybersecurity and the trust? So first, if you think about the security, you have something you want to protect. And you think about the monies and jewelry or whatever treasure. And the first thing you probably will think about is you put it in a safe. And hardware in some sense is the safe here. So you have a crypto algorithm, you implement it either in software or you using whatever programming language, but at the end, you have to rely on hardware to do the computation. The math doesn't do it by itself, it requires physics, okay? And then people very, very soon, they realize that for the same thing, instead of doing these things from software and then implement it using a general purpose computer to do it in hardware, they can do it directly using dedicated hardware. That is the stage I called it is an enhancer. And then you see a lot of small devices, they use hardware to do a lot of computation directly instead of doing a general purpose computer. And finally, in the past decades, as I call this role, becomes the enforcer. So the most significant thing you see here is the trusted platform module, where in some sense it's like a security coprocessor. It does most of the security features of your system in this single chip. And also you have seen a lot of devices, they have these biometric components where they verify your fingerprint, verify your whatever biometric information before give you the access to the system. So this is like building another wall in front of the system, trying to do a admission control. So this is in some sense generally tells you that hardware now plays a more and more involving role and more get involved in security and trust. So then the first thing, this is a lot of us, we know that if you have a safe, then in general, you have a key to open the safe. So this key corresponds to our crypto key if you have a crypto system. So how the key is stored? And most of the people will say, okay, so they will be stored in something called a secure memory. But for hardware designers, there's no such thing called a secure memory. You can always break the system and then trying to steal whatever is stored in the system. And even if they don't have physically, break your system, they can do something called side channel attacks. So this is something similar to when you watch the spy movies. Some people, they can listen to how the safe lock ticks when they try to turn it carefully. So there are a lot of things reported about the side channel attacks, and the side channels including a lot of things. Even sometimes the regular output signals, output results can be considered as side channels. and which information can be hidden behind that. And finally, I'm going to show you some pictures about these things called, these are some kind of equipment called fault injection equipment, which basically they are trying to change the value where you store inside the system, or maybe during the computation of the system, they can change the value. So these things are all really bad things. And then which in some sense, if you don't protect your system carefully enough, like Alex mentioned earlier, so when you design hardware, when you design the system, you don't consider security, it's an afterthought. You think about the performance all the time. So this is like you design a safe, and then you put the key combination in on a sticker, and then put it on top of the safe. It is not safe anymore. And when you do design, if you don't consider security, it's like on the back doors, which we call back doors, where you just leave a couple of holes there. Even if you protect the front very, very nicely, but this safe is not safe anymore. So a lot of these things, a lot of these incidents, and finally, I'm going to mention about something called hardware Trojan. So this all prompts us to this question, which I'm a little bit exaggerating, but sometimes people call, in some sense, hardware now becomes the weakest link in this cybersecurity. Okay. So on the next, I'm going to talk about some challenges or some of the key problems in hardware security. So these are the slides I prepared probably a little bit more than a dozen years ago. And in some sense, it still reflects nowadays what people are doing. In particular, like the recent DARPA program, they mentioned about the 3 key problems, and then they align nicely with these 3 things I'm going to present next. So the first thing I present is because I'm coming from hardware design background. So as a hardware designer, I'm considering my design as my intellectual property. So I want to secure my IP. So that is the one challenge. And it's actually an industry problem proposed more than 25 years ago, and it still remains as a valid, a very, very active research topic. And the second thing here is I design a hardware, and I want my users to use this hardware to do computation, to store data, to collect data. So I want to make sure that this entire process, it will be secure. The data stored in my system is secure, and the computation process is not compromised. And when the device collects data, they're going to collect the correct data. They're not going to be fooled by the attackers. And finally, that is something within the hardware security, community. And hardware itself has a lot of mysteries, has a lot of things that hardware designers, even after these 50, 70 years of development, we still don't quite understand. So these are the things, eventually people say, okay, we can utilize these features, which normally called physical characteristics or fabrication variations. We can use these unknown or uncontrollable and unclonable features to do something to improve our security. And this is, in this society, people call this hardware security primitives. And a lot of things you heard about this lightweight crypto, or lightweight crypto from hardware, or hardware assisted, hardware oriented. So these are all talking about how I can use hardware features instead of a mathematical strong crypto to do security. So in the next, about 8 slides, I'm going to try to elaborate a lot of these things, in particular from information point of view. So what is the information behind all these 3 topics? So first, this information behind this intellectual property protection. And in this case, the player is the bad guy. They are trying to steal your design information. They are trying to steal your IP. And that is the information you are trying to protect. And the most powerful attack, what their tool is trying to do reverse engineering. And at the bottom, it shows a very simple sequence, how you come from a chip, and then they eventually figure out how the chip is built, and people can rebuild it. And this is something becomes very, very convenient because the industry supports this. They provide a lot of very, very advanced reverse engineering tools. And we probably, a lot of us know this Moore's law. So every 18 months, and then the technology, the number of transistors on a single die can be doubled. So what happens is for the reverse engineering tool, they also follow Moore's law. And normally they are 1.5 or 2 generations behind, which means that for today's most state-of-the-art chips, and that after 2 generations or after 3 years, there will be reverse engineering tools that can break it. Or in some sense, today's reverse engineering tools will be able to break the best chip designed 3 years ago. So this can help the actually bad guys in some sense trying to break your chip and then steal your design information, which is the most valuable information from the design. And the people in the past 20 years have developed many mechanisms to protect such information, like embedding or hiding information like digital watermark, digital fingerprint into the design. Like they are trying to do obfuscation, trying to encrypt the design data, trying to obfuscate the circuit, so trying to confuse the attackers, which I'm going to show one example on the next slide. And the split manufacturing basically mentions about, instead of building my chip in one foundry, in one company, if I don't trust this foundry, I can try to split it, build these things in multiple companies, and then eventually I integrate them by myself or through a trusted foundry. So I'm going to show you one example about this thing, which is called gate camouflage. So when you do reverse engineering, you can peel the chip layer by layer and take a very high resolution picture, and then to study how the gate at the transistor level, how the gate is constructed. And when we do a camouflage, so this one shows in some sense like a photo here. And these numbers, 1, 2, 3, 4, all the way to 19 or 20, 19, this shows some of the connections. And with the current reverse engineering tools, they cannot tell whether these connections are really the top layer touches the bottom layer or not. That is the limitation of the tool. And by configuring this contacts carefully, whether they are true contact or they are fake contact, you can use exactly the same topology to implement 3 different kind of logical gates, which basically have 3 different functionalities. So this is one way to do the camouflage or to do obfuscation. And the goal here is trying to confuse the attacker, trying to hide the information. And the second example here, I talk about, hardware security problem is this one, probably we have heard about it. It's called hardware Trojan. And it is one of the key problems to make your IC becomes trusted. And in this context, what the bad guy, they do is they hide some malicious circuitry into the chip. And they can use exactly the same information as you hide digital watermark, digital fingerprint to protect your IP, and now for bad purposes. And also there are a lot of countermeasures, how to prevent, how to detect, and then do the real-time monitoring of the hardware Trojans. And the third example is probably, again, one of the oldest discovery, which is called side channel analysis. And that is for the data and the computation security. So you have your secret key, you have your data, which are stored in the computer, in the hardware, which will be computed, which will be processed by the hardware. So you hope it will be secure, it will be trusted. And however, there are a lot of physical attacks, side channel attacks, and the one I mentioned earlier, like fault injection attacks. And this one shows, this is how the current waves, when the modular exponentiation operation is executed, and then from here on the top, this is like a cartoon, picture here. It basically shows you that what is the key you are using, because when the key value is 1, you are doing more operations, and from there they can tell the difference. And the countermeasures for this is trying to do some better engineering. For example, when you do a design, you want to make sure that for the different key values, the amount of computation you do will be more or less the same. So in that way, you're not going to leak a lot of information. You're not going to leak the key, not leak the data, not leak the current process of your system. And the last example I'm going to talk about here, that will be the last one. That is the hardware security primitives. So in this context, the information we're talking about is, it is something which is behind the very, very complicated, very, very expensive semiconductor manufacturing. And then because of the process, for example, when you dope in the chemicals, there's no way you can make the same chemical exactly the same thickness. And then when you try to apply, for example, the threshold voltage, when you try to design a voltage to on the circuit, on each single gate, you cannot guarantee that they are always the same. And for these kind of variations, it is believed to be something called intrinsic. It is something not human-made. It is very hard to manipulate. And even if the chips from the same wafer, from the same manufacturing line, they are all different. And when I say they are all different, there is no theoretical proof. There is no theoretical guarantee. It is just a general belief. So in the past 50 years, and the semiconductor companies, they have been trying very, very hard to model these variations, and then trying to, in some sense, to compromise them, trying to resolve these variations. But they simply cannot do that. And it started about 15 years ago, and then people working on security realized these variations with this intrinsic, uncontrollable information can be used for security purposes. And some of the information here is, so I listed some of this here. This is the memories thing. And this is the things people call the physical uncountable function, which is the one also in short called the PUF. And for example, in this, the one at the lower corner, this will be 2 5-stage ring oscillators, in some sense like 5 inverters. And the signal will go through these inverters. And the number I put into each of these logical gates is, you can think of them as the delay. And because of the variation, these 2 ring oscillators, their total delay will be different. Like on the top one is 28, and the bottom one is 25. So people can use additional circuitry to collect this information and use this information to create, for example, crypto keys. Like for the same 1 pair of ring oscillators, on one chip, maybe the top one is slower, like in this case, delay is 28. Maybe on the other chip, the top one is faster. And this can be utilized to design 1 PUF bit, either 1 or 0. So the key challenge here is how do we learn, how do we get these variations, and then how do we do this, trying to make them robust against the factors such as operating, environment variations, like the voltage can be fluctuated, it can never be stable, like the operating the temperature can change from time to time, and also circuit may aging. And also the attackers, they are trying to do some attacks, trying to steal this PUF information. So there are also some kind of, you can sense like the game flavor here. You have bad guys, you have good guys, you have attackers, you have defenders, and they are trying to battle, they are trying to fight for some information. Okay, so this is probably the second from the last slide, which I'm going to try my best to trying to show. I think most of the audience here, they are experts in game theory, and I'm just learning here. So if you understand the key things we talk about, the hardware security and trust, you see actually there are a lot of things that they meet the requirements for game theory. So we do have multiple players. We have the attackers, we have the designers or defenders. And in some sense, if you think about, for example, the set channel analysis, you have the information which is your key, and the attackers is trying to steal your key. And as a designer, you want to make your system more robust, more secure, so the attackers may not be able to get that. So that is in some sense who are the players that is well defined. And the information set, as I will mention later, so this can be defined, you can say it is well defined, but it is not quite there yet. So the information, as we mentioned earlier, so if I talk about, I want to protect my IP, so the design details, the test data, the layout, the topology of the gate connection, the logical gate connections, those are the information that I want to protect. I'm the designer. And for example, in the second case, when you talk about the secure data and the secure computation, the key you stored in the system, that is the information. And the attackers, they want to steal that information. And finally, when we talk about the hardware security primitives, the information will be the manufacturer variations, will be those physical characteristics. Those are the informations that the good guys, they are trying to extract from the design process, and then they're trying to utilize that for a security purpose. And I'm going to mention later why this is not complete yet. And the strategy is again, in some sense, as probably people in game theory. So you can never define a complete strategy because the game is dynamic. So people are always going to introduce new strategies. In some sense, they're going to introduce new attacks, and then designers or defenders, they're going to come up with new countermeasures. And based on the new countermeasures, the attackers is trying to introduce new attacks. And the payoff here, it really talks about what kind of problems or what kind of games we're talking about in hardware security. So for example, in the side channel analysis, the payoff here would be for the attackers, whether they can extract your key correctly or not, or how many bits they have guessed correctly. And for the designers, you can probably measure this by how much have I protected my my key here. So in some sense, what is the bar I have raised for the attackers to do to do side channel analysis to reveal the key. And this equilibrium, I mean, like the first presenter talk about it all the time. So this is in some sense the core concept in game theory. And as I'll mention later, so this is probably the things now we pretty much in hardware security, people have no idea about this. So, okay, so now what I'm going to talk about, what is the things which are missing or which are needed for hardware security if you are a game theorist and you want to model this hardware security problem from a game theory perspective. So the first thing is there is a lack of quantifiable information, quantifiable payoff, and what do we mean by quantifiable security and trust? Like Alex mentioned, I mean, this is, so how can you define a matrix to measure the security level, the trust level of your chip, of your IC? So this is something like DARPA has pushed starting by as early as probably 2005. And then eventually people have been trying to work on this. And then for academia people, this is really, really hard in trying to sit in their office, sit in their lab, and then come up with a matrix to measure hardware security matrix. So this really needs an industry to get heavily involved. And fortunately, now we have a new DARPA project, which is called AISS, and that is trying to do, integrate the hardware security primitives, hardware security protocols into the design flow. And their goal is trying to add some tunable knobs, so you can define some, very roughly, some security levels, and then you can, based on your security level, you can compare, I mean, trying to treat security as the same as performance, as area, as power consumption, as delay. And the second thing, which is probably it will be a disappointment for the game series people, is there is a lack of interaction between the two players. And why that is the case, you will say, okay, so you design the chip, and then people, as you just mentioned, so they attack your chip, you have to come up with countermeasures, and then they come up with new attacks, you come up with new countermeasures. That seems to me, it is the interaction. That is the sequential action. But then you have to think about the design time for this thing. And when you talk about in software or in network, and these interactions can be in minutes, or sometimes even in milliseconds. But for hardware, once you're trying to, if I find a bug, if I find a vulnerability in my hardware, I cannot do things like software to issue a patch. Hardware is a piece of fixed thing. You cannot patch them. So there is some kind of promising things called reconfigurability by putting something like a FPGA on your chip. But again, that is still not as close as to software patches. And also in some sense, the goals or the payoffs, like I mentioned earlier, between the attackers and the defenders are not clearly defined. So their interaction is not well defined. So to summarize this, so the key challenge for us to apply game theory results into hardware security, or the challenge for game theory people trying to come to this field to help us, is there's a lack of formal foundations or mathematical foundations to model, for example, the manufacturer variations, to model how much information could be leaked from the side channels, from power, from EM, from radiations, from acoustics, from all these side channels. That is extremely hard. And to conclude my talk, I'm using this, famous phrase, nobody is an island. So basically I'm saying here, no system is an island. So security, privacy, trust issues remains as long as people care about money. You don't take things for free, for granted. And the sad thing is attacking surfaces grows faster than countermeasures. So why hardware becomes the weakest link? That is because crypto algorithms not become secure. They are all behind solid mathematical foundations. And the network security has been started for more than 2 decades. And then the software security, they have been started all the time. And then whenever there is some bad thing, they can issue patches instantaneously. But for hardware, it is very, very hard. And so I mentioned here, if you want to build a secure system, you need a holistic approach where you need to get mathematicians, cryptography, the software, hardware, network, communication, device level, even the material people, and more important, users get involved. And there's a branch in security called, usable security, that is heavily talking about how to make your security usable and then how to educate the user. And finally, to conclude my talk, I'm going to re-emphasize this couple of keywords I mentioned here earlier. So the role of hardware in security is enabler, enhancer, and enforcer. And the information we're talking about here is the information you are processing on the hardware design details itself as the intellectual property, and some of these mystery physical features, like the one we mentioned about fabrication variations behind the hardware. Thank you very much.
Thank you, Gang, for a very interesting and inspiring talk. I have one question from the chat from Charles Camouflage. It says, how can hardware camouflage be used to mitigate hardware Trojan or detect hardware Trojan?
So actually, the gate camouflage, that is the technique to mitigate reverse engineering. And it could be used to prevent or detect hardware Trojan, but as far as I know, there's not such effort yet. And on the contrary, the circuit camouflage could be used to embed hardware Trojan. Because I could build this that way, and then you see it looks like so that is the thing.
Thank you very much. I will thank you, Gang.
Thank you
again. Thanks everybody for attending. I'm going to turn the floor over to Chris, who's going to chair the next session. Sorry. Chris, you're on.
Okay, great. Thank you very much. So we have 5 talks in this next session, and I think we have a pretty tight timeline. So we're going to go ahead and move right into our first talk. So the first talk should be by Fierhan Jia. And I believe that you are online.
Yes.
Okay, so go ahead and get your slides ready. So this is going to be on blocking adversarial influence in social networks.
Try to keep the talks about 20 minutes and 4 or 5 minutes of questions, okay, so that we can stay online. Thank you very much. Thank you.
Could you see the slide?
I can see the slide.
Thank you. Hello, everyone. My name is Fierhan Jia. I'm currently a first-year PhD student at Penn State University. Today, I'm gonna talk about my work blocking adversarial influence in social networks. This is a joint work with Dr. Zhou, Dr. Camouflage, and Dr. Vijay. This is a work when I was a student at Washington University in St. Louis. Currently, social networks are widely used as a media for diffusion, especially for the information diffusion. People and the company utilize the social network to promote the products, to do the viral marketing, and to do some good information spreading. But attackers can also strategically diffuse negative influence through social networks, like they will spread the rumors, the fake news, the misinformation. First, before going to talk about the adversary influence blocking problem, I will quickly and briefly introduce the traditional propagation models and the influence maximization problem. Given a social network, the independent cascade propagation model is that we assume that each edge has an influence probability, and the seeds selected will be active at time 0. And at each time step, each active node will get one shot at activating its active neighbor, and it will succeed with the probability B. Once a node is active, it will stay active. Another propagation model is the linear threshold model. Instead of using the probability of H, it is using the weight W of an H, and the summation of the weight should be less than 1. Each node will choose a threshold at random, and the node will be active if total influence of active in neighbors exceeds the node's threshold. So these are the 2 traditional propagation models. And then I will talk about the influence maximization model, which has been well studied in the past decade. And for the influence maximization model, the problem aims to select a subset of nodes on the network to maximize the overall spread of the influence. And usually we are using the greedy algorithm, which has 1 - 1 over E approximation due to the submodularity of the influence function. And the problem is exactly NP hard to solve. Even computing the exact influence, it should be NP hard to solve. In contrast, we are investigating the problem of limiting the diffusion of negative influence by blocking node. In cybersecurity, we can consider this as the spread of malware on the network. In public health, we can consider it as the spread of disease. In social networks, it might be the fake news or the misinformation. Previous work of influence blocking presumes that a diffusion process is spreading, typically either from a subset of nodes or from a node selected according to some known distribution. And the goal is to block its diffusion path through either selecting a set of nodes or edges. It is also effective to detect the fraud information using some detection techniques. But our question is that, could we protect those vulnerable nodes or accounts or peoples in the networks in the advance? So this is our problem. We called it the adversary influence blocking, AIB problem. So what we would like to do is to block some nodes. We will, in practice, we can assume that we are imposing using some restrictions on a subset of computing devices, or even isolate this from the internet, or inoculate the people in pandemics. The problem can be naturally considered as a stacker broker game, in which the defender will first choose a subset of nodes to block, which is the SD, and it also has some budget, which is KD. The defender's utility is the negative influence because it is aiming to minimizing the negative influence caused by the attacker. The attacker will move next to select a step of seed nodes to begin network diffusion. The adversary's goal is to maximize its overall influence, whereas the defender aims to minimize it. So the defender, we can have an example of the defender-attacker interaction. Here we are using the greedy algorithm of the attacker's algorithm, and we are using the linear threshold to propagate the information, the negative influence. And here the attacker's optimal strategy should be node 6, 13, and 14, and the utility of attacker should be 12.73. But if we have we have defenders, we can first protect the node 4, 6, and 18, and then the resulting utility of attacker can be limited. This problem is significantly more difficult than the traditional influence blocking problem, since we are now allowing the attacker to be adversarial, to be smart, because they can make their own new strategy after witnessing the defender strategy. And this problem is an extremely challenging bi-level optimization problem, which the defender strategy has an exponential space. It is a combinatorial problem. The attacker strategy is influence maximization process, which is an NP hard problem. Even calculating the influence is NP hard, as we talked before. And usually we are using the Monte Carlo simulation to estimate the influence. Our idea is that could we simplify the attacker's model? What the model we are looking at is the maximum domination. We approximate the influence maximization procedure in the lower level problem by maximum node domination. Although this problem is still NP hard to solve, but we can solve it using the integer linear programming. And so we can make use of this together with some constraint generation techniques to develop our first practical solution. And we denote this problem as KMaxVD. The maximum domination problem is that we will find a subset of nodes which maximize the cardinalities of the dominated nodes. And here is the example. If we choose these three nodes, all of these neighbors will be influenced. We can derive this problem as a mixed integer linear programming. The first set of constraints are the interdiction constraints because the attacker will not select the node which is blocked. And the second constraint is the budget constraint. The last constraint is the influence constraint, which denotes whether a node is influenced or not. So this is the best response function when the attacker has witnessed the defender strategy X. And then we can write down our optimal influence blocking problem. The defender's optimal problem can be written as the minimizing the total influence subject to the defender's budget, and Y is the best response of the attacker strategy. The problem is very hard non-convex bilateral problem. So we would like to linearize some term and find another method to solve it. And our method is that we will use UA, which shows the upper bound of the attacker's utility. And we still have the defender's budget, but we linearize the minimization term using the big M notation and the binary variable B. So for this problem, if we have all the attacker strategy, we can minimize the the utility of the attacker. However, this problem is still intractable because the Y space is combinatorial, so we cannot solve it in any solver. The method we are using is the constraint generation method. We replace the attacker's strategy space Y with a Y hat. It is a small subset of attacker's strategy. The main idea of this algorithm is that we will first start from a subset of attacks, and then we will solve the restricted masters problem using the subset of attacks Y hat. And we can have a solution here. We can have a solution here, but it would not be the optimal solution. So the attacker can generate the best response to X, which will return a new attack Y. And we will add this Y to the Y hat. And during this process, we have our upper bound and lower bound. When the bounds meet, we can get the optimal solution. And we also improve this algorithm by a good pruning method. We can prune some irrelevant constraints, like when the T equals 1 for some attacker strategy. We can just ignore those constraints with T equals 0. So the last problem can be solved in 46 to 65 node network, but it is very time consuming. So what we are thinking is how to speed up the algorithm, how to approximate the algorithm in a better way. So this is our next algorithm. The idea of this algorithm is that we first do the LP relaxation for the inner problem and take the due of the relaxed inner problem. Finally, we linearize all the nonlinear terms using some operation research techniques. Here is a single level mixed integer linear programming for the defender to solve, which is much more efficient. And we also have the extension versions. The weighted version is the version that we assume that each node in the social networks is associated with a weight. The weight is sampled from 0 to 1. It is reasonable because the node in the social network has different importance. And we also have our H blocking version. Although we can speed up our algorithm through the diff MILP, but it can still not scalable to large networks. We have the computational bottleneck that the number of constraints will grow linearly with the number of nodes. And when the MILP is very large, the solver cannot solve the problem. So we have a very heuristic pruning method. We will prune some least important nodes in the strategy space. Just like we can rank the nodes by the degree centrality, and we just consider the strategy space from top 200 nodes. And we will compute this prove the MILP. This can solve some thousand node network, and it is really important in practice. And then I will talk about our experiment. We have done extensive experiments. We show that our approach is more efficient for computing influence blocking nodes than some previous alternatives of influence measures. We are looking at the synthetic networks like the random node network, the small world network, and the parallel networks. We have used the real networks like the email core network, the hamster network, the sampled Facebook and arrow email networks. We are looking at our defending algorithm, the K-max. We are using the attacking models like K-max-VD, the influence maximization with different propagation models, and the weighted version of influence maximization. For the baselines, we are using the degree centralities, the petunias centralities, the page rank, the influence maximization, etc. And we are using our algorithm of constraint generation, the diff MILP, the weighted version, and the corresponding heuristic pruning version. So here is the first set of experiments, which is the constraint generation versus the diff MILP. The gap is showing the gap between the faster utilities. When the gap equals 0, implies the CG algorithm computes the optimal solution. We can find that our result of diff MILP is quite close to the optimal CG solutions. In the cases with some small gaps. But our diff MILP has significantly better runtime than the constraint generation. So it is our primary defense strategy. Here are the results of the synthetic networks of the diff MILP and diff weighted version. We can see that our algorithm works best through all the kind of heuristics. Since we evaluate our pruned MILP, because the real networks are very large, and we are using the degree centralities as the pruning strategy. So we just compare with the degree centralities. It shows that when we use our pruned MILP, it can significantly improve the centrality method. So which means that we can really protect our networks in the like the 2,000 node networks and 1,000 node networks. The last set of experiments is showing the weighted version of pruned MILP. So when the nodes have the weight, the difference between our algorithm and the original centrality algorithm might be more significant. So it is also showing the efficiency of our algorithms. All the experiment results shows that our proposed defense approach are effectively limited the spread of misinformations in those adversary environments, although there are many different kind of attacks, and it will outperform other baselines. But there are still many things to do in the future. We can have better solutions since our solution is still a good heuristic. There should be better heuristics, and we do not consider the graph, the dynamic graph. We are just consider the static graph. We assume that all the nodes, the age, are known. But in reality, the social network graphs are dynamic and some of graph information are not known. So these are still the challenges to solve. This is my final slide. Thanks for your attention. I also appreciate the hard work of the organizers. That's it. Thank you. Do you have any questions?
Hey, so thank you very much. I think we have time for a couple of questions. So let me actually start with one. So in some of these examples, one of the core problems seems to be that it's not actually clear who the adversary is and what an adversarial signal is, especially in some of these fake news kinds of settings. Does your model have anything to say about that, or have you thought about how to incorporate that into your model at all?
We currently do not specify which exact the attacker will be. So we are thinking about a general solution to the general adversary attacks.
Okay, so we also have a question in the chat. To what extent have you looked at architectures and connectivity of practical social networks and use these for the experiments? They have very special topologies, and most importantly, they are dynamic. I think you addressed that a little bit at the very end, but maybe you have a few more things to say about that.
The network structure. Yes. Our algorithm is still a heuristic. We select a lot of different network structures, and our algorithm really works in different network structures. But since it is a heuristic, so maybe it will. There might exist some network structure it does not work well, but I think it deserves trying to try our method. But I think it's a good question. I think some of the network structure might be exploited, and we might have better solutions for this problem. So it would be the future work.
Okay, thank you very much. I don't see any further questions at this point, and I think we're out of time. So I'm going to ask our next speaker to go ahead and get set up.
Thank you.
So this should be Xiaobi Ma.
Yeah, hi. Hi. Thank you. So shall I start?
Yes, go ahead and get started when you're ready.
Let me find my slides. Okay, so hi everyone. So everyone could see my slides now, right?
Yes, I can see your slides.
Okay, yeah. So thank you. So my name is Xiaobai Ma. I'm a PhD student at the Stanford Intelligent Systems Lab. So today we're gonna present our work on the normalizing flow policies for the multi-agent systems. So this is a joint work with me and my lab mate Jayesh and my advisor, Professor Kokendorfer. So we focus on the multi-agent interactions in the deep reinforcement learning domain. So the key motivation of our work is the understanding of that the multi-agent interactions require complex action distributions. This could come from, for example, the imperfect information such that the agents could have multimodal behaviors from different latent variables. And also in strategic interactions, agents need to have this complex action distributions to avoid being predictable to the other agents. However, this is often ignored with most of the current work is working with the discrete action space, where a categorical distribution is enough. However, so we realize that the current common practice of using a diagonal Gaussian policies as agents' continuous action distributions is not enough for such complex interactions. So we first give two examples of how the complex action distributions could show in our daily life. So consider you driving through an intersection with traffic lights, and when the yellow light turns on, you could the conservative drivers might apply a brake and stop for the intersection, where a aggressive driver could accelerate and trying to go through intersection before the red light is on. So here, clearly there's two modes in your action distributions. So in an even more complex scenario where there's two human drivers are trying to switch lines in the highway, so they need to do this back and forth interactions in order to avoid collisions. And in this case, their action distribution could be so complex that there is not even a distinguishable modes in their distributions. So, so before we jump into our approaches, we would like to first do a little bit review on how we could actually model complex distributions in deep learning. So first, and it's mostly used, we could use a Gaussian mixture model where we have several numbers of different Gaussian distributions, and at the sampling time, we first sample which distribution we're going to use, and then we sample our actions from that distribution. So it's a classic, and it's very easy to analysis. However, it's still limited on the classes of distributions it could actually represent, and also it needs some prior knowledge on how many nodes you're going to use in your Gaussian. So also we could also use a sample of models where we could have a population of distributions, and similarly as the mixture of Gaussian, we could first sample which distribution in the population we're going to use, and then we sample from that distribution. So we will got more flexibility as we increase the population size. However, it's also very expensive to maintain a large population of distributions. So most recently, there are some like even fancier works on like using latent variable models, such as a variational autoencoder, where we could firstly sample a latent variable from some simple distribution, and then we could sample our output based on that latent variable. So it's much more flexible, and it could almost approximate to any distributions. However, it's very hard to optimize since it doesn't have a tractable marginal distribution of your output. So, and finally, what we proposing to use is so-called a flow model or normalizing flow model, where similarly, you first need to sample a latent variable from some base distribution, and then you apply a deterministic mapping from your latent variable to your output. So it's also very flexible, and even better, it has a tractable marginal distribution. However, it also has some disadvantages that, like, they have some limitations on the structure of the mapping. So more on the flow models. So the basic idea is to transfer a simple distribution to a complex one through invertible mapping. So the way you do that is like, so first you sample your latent variable from your base distribution, and then you apply the inverse mapping to Z to get your output. Then your output S could be regarded as sampling from a complex distribution. And to calculate the probability of X, you need to do the mapping from X to Z to calculate your latent variable, as well as the determinant of your Jacobian of your mapping. So in order to make this calculation of probability efficient, the key point is to decompose your invertible mapping as a composition of multiple layers of simple invertible mappings with triangular Jacobians. So in order to use the flow model as a policy, you need to condition its output on your state or observation. So we propose to do this by using the state as an extra input at each layer of the mapping. So more concretely, here is an example of an illustration of how we using the real MVP, which is a successful normalizing flow model as our base model to make it as a flow policy. So here again, we sample our latent variable Z from the base distribution, which could usually be a diagonal Gaussian distribution. And then at each layer, we divide the latent variable into two parts. So for the upper parts, we do a direct identity mapping to the next layer of the latent variable. For the lower part, we do a scaling with translation to get the next layer. So the scaling factor and the translation factor are calculated using the neural networks, which takes the input of the state and your upper part of your latent variable. And in the next layer, we switch role of the upper part and the lower part. So by applying a sequence of multiple such layers, we could finally get our output distribution, our action, whose distribution could be very complex. So again, so we first gonna design some experiments to test whether our proposed flow policy could actually learn such represents complex distributions. So remember to the from the two examples. So the first example is like in the traffic light intersection. So this plot showing the sampled action distributions with the policies we learn. So we train these different like baseline policies as well as our proposed policies using the behavior cloning using the expert trajectories. So the baselines we are comparing, including the Gaussian policies, the diagonal Gaussian, and also the CG here is like the Gaussian policies with full covariance using the Cholesky decomposition. Also, we have the mixture of Gaussians and also a mixture of Cholesky Gaussians. So yeah, so basically by here, the plot showing here is like the horizontal axis is like the longitudinal position, and the verticals is the actual actions, which is the accelerations of the driver. So here, if you looking at the expert trajectories, you can see clearly as approaching the intersection, which is represented by this gray line, we have a clearly distinct modes on their accelerations. So, and we could also see that even by visually, we could see that the real MVP policy is kind of best captures this multimodal distributions from the expert. So here's apply the same technology of behavior cloning into the traffic weaving from the expert trajectories. Because the distribution is so complex, so that we could not determine the quality of the learning just visually. So we calculate the first resistant distance to compare the distance between the distributions of the positions rolled out by the expert policy and as well as the learned policies. So again, we could see that the flow policies is closest to the expert distribution, which has the I mean that it's like it has the lowest first resistant distance with respect to the expert trajectory, like across the majority of the time steps. So moving to the reinforcement learning and games domain, we first to see that whether our proposed structure could actually learn the required complex distribution through the reinforcement learning. So first we test them on a bunch of the continuous single step 2-player games. So those games are chosen so that they have a known and unique Nash equilibrium, and an ideal policy should be able to learn to converge to the Nash equilibrium distributions. So, so this label shows like the rewards of the games. So here, so on the left, this plot showing the Nash equilibrium distribution of each game, as well as the learned distributions from the different policies. So, and in this table, it shows again like the first resistant distance to the learned action distribution to the actual Nash equilibrium distribution. And from the plot as well as the table, you can see that the flow policies actually learns the closest action distribution to the Nash equilibrium. So finally, we test our structure in a even more complex high-dimensional domain, where we design these so-called the farm security games. So imagine you have a line of farms where you have the plantations growing distributed in this region, and the attackers are kind of like the birds which gonna to fly into this region and choose a place to eat some crops, and the defenders gonna place these scarecrows to scare the birds away. So the state of this game would be the locations of the crops, and the actions would for the attacker would be the target location where the bird's gonna fly through the closest boundary and perpendicular to the boundary and fly to the target region and fly back. So and also the action for the defender will be the target location where you're gonna put down your scarecrows. So the reward for the attacker will be that they're going to get more reward if they have more crops in their target area, and they get some penalties if they meeting the scare arrows in their path. And for the defender, they get rewards for the scarecrow they placing could actually meet the birds. So after we applying the multi-agent reinforcement learning algorithms to train these policies. So here is an example of the learned distributions from different policies. So in the very left column, here are the scatter plots of the action samples from different policies. So it's kind of hard to tell here, but so the green dots are the locations of the food, and where the red dots are the sampled target locations of the attackers, and the blue dots are for the defenders. And we also plot like the action, the probability density function of the action distributions. So here is the defenders one, and here is the attackers one. So first we would like to consider what is an ideal action distribution of the defender and the attacker. So because they are in this competitive setting, so both players need not to be predictable by their opponent. So for the attacker, their target is to learn a distribution that they could cover as much as food regions as possible. And for the defender, the most efficient distribution will be they trying to block all 4 edges in this region. So for let's first look at the Gaussian policy. So for the attacker, it just learns kind of a uniform distribution. And for the Gaussian defender, is due to its representation limitation, it only learns to block 1 edge of the region. So for the GMMs, Gaussian mixtures, and for the flow policies, they kind of doing better here. However, in the second example, we're increasing the incline angles of the foods, where even the GM policies, because now the correlations between the X and Y coordinates of the foods are strong, so that each diagonal Gaussian in the mixture model could only cover a very small region of the food. So in this case, the attackers from the GMM is also becoming relatively predictable. However, the saturation doesn't happen to the flow policy. It's still is very flexible, and it's also learning to kind of perfectly cover where the food are. So, but those are just like visual and examples. So in order to actually quantitatively compare the different policies learned by different policies, we're using the alpha rank algorithm to compare those different policies. So the basic idea of alpha rank is to so basically form a Markov chain, which each node is using, each node represents a choice of the combinations of the defender policies and the attacker policies. And the transition probability is dependent on the returns when they playing against other nodes. So here is like the results where we could see that so the S1 stands for the defender and S2 stands for the attacker. And the orders like 0 stands for the Gaussian, 1 for GMM, and 2 for the flow policy. You can see that the combination of using the flow policy for both the defender and attacker forms a sync node in this Markov chain. And also we can see that the final stationary distributions would apply all its probabilities to use the flow policy as both the attacker and the defender. So yeah, so in summary, so the multi-agent interactions can result into complex agent behaviors, and even the Gaussian mixtures might not be sufficient for modeling the required complex multi-mode action distributions. And in this work, we show how the conditional normalizing flow models can actually be architectured to gain the significant performance improvements at such modeling problems. So that ends my presentation. Thank you. And are there any questions?
Okay, so thank you very much for your presentation. Let me ask if there's any questions from the audience. So one quick question while we're waiting and seeing if there's any others. So you had a couple of examples where you had expert baselines for these complex behaviors. Do you have a sense of how reliable those might be? It seems very difficult maybe for a human to actually be able to capture these sort of complex distributions. So do you have any sense of that?
Oh, okay. So yeah,
I guess you're examples and so forth.
Yeah, sure. So yeah, I should mention that. So for the driving, so in the first example, so in this the traffic lights, maybe I should here. So yeah, so here is like the expert is actually what we hand coded the behaviors of like our understanding of how human gonna react in the interactions. So this is more like a synthetic example, just showing like the representation power of the flow policy. But for here in the traffic weaving, we actually use like a data set which collected from like real driving behaviors from the humans. So here like we only have the sampled trajectories and actions from the humans, and so we compare the sampled trajectory from the learned policies with those realistic data collected from the human. So here like the expert is actually real human drivers. So I mean, does that answer your question?
Yes, I think so. Don't see any other quick questions. So we're actually at our time. So we're going to go ahead and transition to the next talk. So thank you again very much for your presentation.
Thank you. Thank you, Chris.
And our next speaker should be Ahmed Hamida. Go ahead and get set up.
Thank you, Chris. Can you hear me?
I can. I can't see your slides yet.
Okay.
Okay, I can see your slides now, so go ahead and get started when you're ready.
Thank you. Thank you, Dr. John, Dr. Chris, and hello, everyone. My name is Ahmed Anwar. I am a postdoc at the Army Research Lab. And today I'd like to present this work on software diversity for network security using game theory. This work is done with Dr. Charles and Dr. Nandi here at the ARL, and joined with Dr. Chris Kickenveld at University of Texas at El Paso. So I will start talking about the potential benefits of diversity, which motivated this work to enhance network security, and define the research questions that we are investigating, and then talk in specific about the generic game model we developed to study the effect of diversity on network security. So diversity as a design concept is implemented in different domains such as financial portfolios, also in physical systems, and in more heavily implemented in security applications to enhance performance and the resilience of each of those systems. For example, a diverse network is more immune against zero-day attacks and would avoid a whole point, like single point of failure for the network, and reduce the attack surface as well. It also limits the ability of attackers to discover the components and address threats such as scanning and fingerprinting, which are the first steps that an attacker would take while launching a more advanced attack. Also, diversity would prevent the attacker from reusable exploits to compromise the whole network. However, diversity is not cost-free, and it adds to the network overhead and may face some compatibility issues when implemented, and requires more effort in network operational cost and configuration. And this proposes a trade-off that we are interested in studying. And more importantly, we want to see how can we capture the direct effect of diversity on network security. So in modeling that, we assume that each host or machine in the network can be represented as a node on the network graph, and it would be assigned some sort of software. And I would like to start by highlighting that we don't refer to software diversity in this context by simply or limit the definition to source code diversity. But it can be implemented in different levels, such as diversity over operating systems, applications, even hardware. So this, I would consider it a generic formulation and can be implemented on different levels for security. So each node will have a set of vulnerabilities associated to it, depending on what software type it will be assigned to. And it can be seen to diversify different software types over the network graph. We are having some form of a graph coloring problem with some modification. And the color set is what set of software that we have and the defender is willing to use on top of that network. Playing games on graphs are known to be hard, and however, in this model, we don't play the game of allocation of the software. The role of the defender is to determine the level of investment in diversity that he's willing to take. And the task of the allocation is actually done by the graph coloring algorithm. So more specifically, the defender would, as I just said, decide the number of colors that would be sent as an input to the graph coloring algorithm. Then the algorithm task would return the allocation and assign different softwares to each to the different nodes. And this would definitely reduce the complexity of the defender problem and makes the game complexity independent of the network size, which is usually the case when playing games on graphs. So this is a first step we were aware in the modeling to avoid so that we keep the game tractable. However, the trade-off of diversity faced by the defender is that it leads to high security level when he diversifies more using more types of software, but this also maximizes his cost. And this is all captured through matrix multiplication, where we have a software vulnerability matrix that tells us what software is associated to what vulnerability, and also a network software, which is the output of the graph coloring algorithm. And in our work, we started by assuming that these are deterministic and known matrices. However, they can be directly also transformed into stochastic matrices to capture other security scenarios where the information is not perfectly known or complete. On the attacker side, the attacker is probing the network to gain information and exploit possible vulnerabilities. So each probe can exploit a subset of vulnerabilities in the network. And the attacker would need to decide how many probes basically he would like to use in order to map out or learn information about this network. The more probes that he would use in the attack, the more number of nodes that he can possibly exploit. However, this also leads to more interactions with the network, more cost for the attacker, and more likely to be detected earlier by intrusion detection systems. So this is the sort of trade-off the attacker is facing. So based on that, we can define the payoff utility functions for each player. There is a trade-off captured in two terms. One is basically, which is the shared component between the payoff function for both players, capture the reward and the cost due to the network security represented by the average size of the exploited subgraph that can be compromised based on the action profile taken by both players. And the other component is a subtracted cost term associated with the different actions that each player select. So this leads to a finite non-zero sum two-player game, and it can be solved finding at least one point of Nash equilibrium using sequential quadratic programming based on quasi-Newton technique, which is available in literature in terms of mixed strategies. So the algorithm would be to diversify, start with defining the action spaces by defining the set of softwares available to the defender and set of probes available to the attacker. And then for each, we have for each possible combination of softwares, we can have the graph colored and have our network vulnerability matrices defined. And then for each possible probe played by the attacker, we can define two payoff matrices for this finite game for each player, and then we solve the game. So we plot the attacker reward to evaluate the effectiveness of the diversity algorithm that we are defining. And we see that as the number of available software types increases, the defender can color the graph more efficiently, and then the software diversity would reduce the attacker reward. Nash equilibrium strategies may lead the defender not to use all the available colors to limit the cost. And also, since more number of software may introduce new vulnerabilities to the network. So it's not the best in every case to increase always the number of software used in the coloring process. So the attacker reward when the defender also deviates from his Nash equilibrium, as you can see here, yields a higher reward for the attacker, even higher than the monoculture case where there is no diversity used at all. And the defender reward, as shown in the right figure, is plotted at different number of software types for Nash equilibrium defensive strategy for both sides. And the defender reward, as seen, is non-decreasing as the number of available software types increase. The effect of cost values, the defender reward decreases as the cost increases, since the defender tends to exclude more software types to avoid the defender paying higher cost. While for the attacker, reward increases as the defender diversity capabilities are limited as we increase the cost for him, while the cost per probe is fixed. And here, when we change the cost per probe, when the cost per probe is low, the defender reward is stably low, as the attacker can afford the cost to use all his probes in the attack. However, beyond one, the attacker reward starts to increase as the attacker starts to incur more cost per probe. In our work also we looked into, although the modeling of the game avoided the game complexity to depend on the network size. However, it's still exponentially complex, grows exponentially in the number of strategies for both players. So since the attacker and the defender chooses the number of software that he wants to use or the number of probes, the algorithm still needs to consider the different combinations of those softwares. So another complexity reduction step can be done by actually weighting every software type depending on how much vulnerabilities he can or it can bring to the network. And also we can weight the probe type depending on how many exploits it can, how many vulnerabilities this probe type can exploit. And we, instead of considering all the possible combination, we simply prioritize according or sort the software types according to their benefits. And from the other side, we can consider a worst case scenario, assuming that the attacker would always consider the most damaging probes. And finally, we compare the reward out of the two algorithms. And you can see here that they are leading to a very comparable performance. However, in the comparison of the runtime of the two algorithms, there is a huge reduction, and we have avoided the increase exponentially in the number of software types, since we are not considering the combinations of all the possible software types. So to conclude, we have developed a game model to study the interaction between the defender and the adversary, specifically to see the effect of software diversity as a defense strategy for the attacker. We exploited the graph coloring algorithm to deploy Nash equilibrium over graph. And we also proposed the complexity reduction approach to obtain Nash equilibrium for diversity of large scale networks, considering larger number of colors or larger number of softwares. And our ongoing and future work, our research group has already been working on partial observable games and games with incomplete information. And we are also considering this for that type of game, as in this first paper, we just considered the perfect information scenario. And I'd like to thank you and take any questions.
Okay, thank you very much. We do have a few minutes for questions, so please go ahead and post your questions in the chat or raise your hand. Okay, while we wait to see if there's any other questions. So maybe you could talk a little bit about how you might generalize this if you had more than one software that was running on a particular node. So I think you're base model assumes that you're just coloring each node with a single color. Of course, in the real world, nodes are going to be running many different types of software. So would this be able to generalize to actually coloring nodes with multiple colors or something along those lines?
I would say yes, we can do that. It can be extended to multiple colors, since at the end we consider the resulting attack graph and capture that through the network vulnerability matrix, which defines the payoff matrix for each player. So I would say yes, it can be considered, and it wouldn't be a limitation. It's a very good idea. Thank you.
Okay, so any other questions from the audience? Okay, I don't see any other questions right now. So thank you very much.
Thank you, Chris.
We're going
Thank
to
you so
wait
much.
for just a couple of minutes to start the next talk, so we don't get too far ahead of schedule. So we do have a couple of minutes before we're supposed to start that talk. So go ahead and get set up, and I'll let you know when to begin. Okay, thank you, Ahmed, one more time.
Thank you all.
I should also note, so if you have questions for any of the previous speakers that came up to your mind after the official talk ended, I think you can go ahead and post those in the chat, and the speakers may be able to respond to those as well.
Hello?
Yes, hello. So you can go ahead and get set up and start sharing your slides. We'll start in about 2 minutes.
Hello?
So I can hear you.
Please, I don't know if it is me you are waiting for. Something has happened. I cannot see any video now.
You can't see a video, is that what you said?
Okay, I can see now. Do I have the floor, please, Professor?
You do, so I don't see your slides yet. Are you going to share your screen?
Let me share the screen.
And forgive me, so how do you pronounce your name?
Please, sir, can you see my slide now?
Yes, I can see your slides now.
Okay. Thank you.
Okay, so yeah, please go ahead and get started whenever you're ready.
Okay, thank you. Good morning. I am Olivier Semonier. I am a PhD student of University of Chartres in Cameroon in conjunction with the Avignon University in France. I did this paper with my supervisors, Professor Hayek, Dr. Kamwa, and Professor Dogui. The title is Partially Observable Stochastic Game for cyber deception against network epidemics. A partial observable stochastic game is a repeated game for which transitions are probabilistic. That means that no player can monitor the transitions. An epidemic, to make it easy, is any token that can spread over a network. We have, for example, diseases like COVID-19, rumor in social networks, botnets in the IoT. Traditionally, to study an epidemic, we divide the population into compartments. For example, we can have S compartment consisting in susceptible individuals, those who can carry the disease but do not carry it. Now, we have infected individuals, we have resistant individuals who are not vulnerable. We may also have other compartments depending on the type of epidemic. We use a zero-sum partial observable stochastic game and deception to overcome an epidemic in a network. Our model of partial observable stochastic game is not a classical model because one player does not know the state of the network. It is neither a one-sided partial observable stochastic game because no player observes the action of the opponents. After this introduction, I would like to present you two things concerning the related works. I would like to describe the problem, describe the model, describe the solution we should normally have to this problem, present an important tool to reach the solution, which is the value backup operator. And in the conclusion, I would like to say something about our future work. While studying network epidemics, the major question to answer is to know how should nodes behave. Beyond this question, it is supposed that all nodes will have the same behavior. So, to formulate, in other words, the question is, what is the best same behavior for nodes in order to stop the epidemic in the network? But there is another standpoint to see epidemics in that we can use to see epidemics network. We can see the stopping of epidemic as an attacker-defender game. Doing so, we know that we have in memory that in attacker-defender game, an important tool is used in partial observable stochastic games, classical one, and one-sided partial observable stochastic game, which is the heuristic search value iteration. But the heuristic search value iteration has never been presented in our particular model, which is neither a classical partial observable stochastic game nor a one-sided. So our work is especially a novelty because we address the stopping of an epidemic from the perspective of a partial observable stochastic game, and which partial observable stochastic game is not a type we used to know in the literature. The problem is a rational virus spread An attacker is silently spreading a worm over the network. It can be, for example, to prepare a distributed denial of service. This is possible because many IoT users do not customize their passwords. A defender, to mitigate this propagation, incites users to customize their device's password. They also make use of a fixed number of honeypots. They allocate honeypots on some edges of the network, time slot after time slot, to deceive attacker action. But each node too can take a random move. For example, an infected node can decide to accept the patch proposed by defender at probability alpha, certain probability alpha. A susceptible node would customize the password, his password, at a certain probability row and become resistant. So the problem is to find an optimal strategy for honeypot allocation, an optimal strategy for defender for the honeypot allocation. The model we use, as we said, is a partially observable stochastic game. This is the epidemic model we use. It is an SIR epidemic. We have susceptible nodes. Any susceptible node by an infection can become infected. Any infected node that accepts the patch can become again susceptible. But any susceptible node which decide to customize the password may become resistant. Here we have an example of time slot. A time slot consists in 2 stages. At the beginning of the first stage, we have 3 infected nodes, 1, 2, and 4. 1 resistant node 7, and the other nodes are susceptible. Attacker decide to propagate the virus from any infected node to a susceptible neighbor. At the same time, defender allocates 2 honeypots. It's the number of honeypots at his disposal on 2 edges of the network. Attacker has decided to propagate from 1 to 3, from 4 to 5, from 2 to 6. But defender has allocated 1 honeypot on node 4, 5. So defender will detect the attack and kill nodes 4 and 5. Propagations to 1 to 3 and 2 to 6 are not detected, and nodes 3 and 6 will become infected. After that, there is the second stage. Some infected nodes 1, 3, and 6 decide to become susceptible. Node 5, which is susceptible, decide to become resistant. This is our game model. G is a network. It consists in devices and edges. Z is a set of possible states of the network. Infected, each node can be infected, susceptible, or resistant. A1 and A2 are the actions profile for defender and attacker. Any defender action consists in choosing a certain number of edges on which he will deploy the honeypots. He should take care that the honeypot should not be on no edge that links to a resistant node because it's not useful. Any action of attacker consists from any infected node to choose what edge he will propagate, through which he will propagate the virus to a susceptible node. O is a set, is the observation space. We assume that the defender is aware when any node becomes susceptible or resistant. T is a transition function. We have 2 types of transitions. The first transition corresponds to the first stage of the time slot. A susceptible node that receives an undetected infection will become infected. An infected node that propagates a detected infection will become susceptible. The other transition is a probabilistic one. R is the defender reward associated with the device transition. It is good to remind that our game is a zero-sum game. When any infected node becomes susceptible, defender has a reward R2. The reverse transition produces a negative reward. When a susceptible node becomes resistant, the defender has a reward R3. We have the other parameters. B0 is a belief of the defender at the beginning of the game. We notice that for alpha, probability for transition infected to susceptible, rho transition susceptible to resistant, alpha 0.5 and rho 0.1. After 140 iterations, all nodes are resistant, but the problem is the cost to become resistant. The solution is an optimal strategy for defender. Defender does not know the state of the network, so the strategy of defender, the mixed strategy of defender is a probability distribution after his action profile. But the probability distribution for attacker should rely on the state of the network, since attacker knows the state of the network. Defender has to update the belief, his belief time slot after time slot. That updated belief relies on the actual belief, on the transition function, and on the strategy of attacker. Both players can decide to play a strategy according to the history. So we derive here a strategy. The history-based strategy is an application that maps to any history, a strategy for any stage of the game. The payoff, the total payoff, the expected total payoff at infinite horizon of the defender is called the utility. We consider here a discount factor gamma. Defender should suppose that attacker will play in order to minimize this utility. So we take into consideration the minimal utility defender can realize when he plays strategy sigma 1. This minimal utility is called the value associated to the strategy sigma 1. So the objective of defender is to maximize that minimal utility. In other words, to play the optimal value of the game, which is this. An important tool to calculate the optimal value is the value backup operator. To understand it, suppose that we have reached a certain stage of the game, and at that stage, defender wishes to know which strategy P1 to play, and attacker wishes to know which strategy P2 to play. Defender has a belief B. If defender takes strategy P1 and attacker strategy P2, we have this immediate reward at that stage of the game. But after this stage of the game, attacker and defender are engaged in a new infinite horizon game that we call subsequent game. We suppose that we know the optimal value of that subsequent game. If we know the value of the subsequent game, then the optimal value, then we have the subsequent rewards. When we add the two rewards, immediate and subsequent, it is the reward of the total game, the game of the stage we have considered, and the subsequent game. We do not forget the discount factor. So if we call HV the optimal reward of the total gain, and we are considering a certain operator that we call value backup operator. An important property of the value backup operator is that it is a contracting mapping. From this property, it is clear that if we have an upper bound and a lower bound of the value of the gain, iteration after iteration, given any positive number epsilon, we are sure to reach an epsilon optimal value of the gain. To conclude, we should emphasize on a certain fact. The heuristic search of value backup iteration normally is not scalable. To improve the scalability in literature, an important tool is used. It is the double oracle. With the double oracle in lateral movement, we can apply it for something like 40 nodes. But here we don't have a lateral movement. We have an epidemic spreading over the world. And that epidemic aspect makes intricate the scalability because the number of states increase exponentially in the number of nodes. We wish to better improve the scalability of the heuristic search value iteration in our work in progress. Thank you very much.
Hey, very good. So thank you very much for your talk. Let me again ask if there's any questions from the audience. We do have time for a couple of questions. This is a little bit of an odd question, but since you raised sort of the epidemiology motivation as well as the cybersecurity one, I wonder if you have any thoughts about what might be an analogy to a honeypot as a kind of detector or sensor in a biological epidemic. Of course, we're all very interested in stopping biological epidemics right now. Can you think of any strategies that might be similar in those kinds of contexts to the way that we use honeypots in a cybersecurity context?
Are you asking the importance of honeypot in cyber deception, please?
Well, we use honeypots in cyber deception, certainly. So they serve as, well, one of the purposes they serve is as a detector. I wonder if there's any analogy to that kind of detection strategy in a biological epidemic. So actually tracking a virus like COVID or something like that. Would there be a way to implement that kind of strategy for detection?
In fact, the use of honeypots here is not really to track the virus. It is to deceive attacker. We suppose that an attacker is silently spreading the virus. So attacker is playing strategically, and defender has to use another strategy to mitigate attacker action. The honeypot here can act as, it is a certain tool. In our paper, we consider that it is a certain tool that can allow defender to know that this node is infected, and therefore this defender can decide from his own to cure the node. Because a defender cannot take this decision if he's not sure that the node is infected.
Okay. Thank you. So any other questions from the audience? Okay, well, thank you again very much for your talk.
Thank you, sir.
So we're going to move on to our final talk for this session. Yuhan?
Yes, I'm here. So I will start to share my screen.
Go ahead and get ready.
Yes. Yeah. There we go.
I have some issue. Okay.
Is it look good? I'm sorry.
So I can see your screen now.
Okay. Can you see that?
Yes.
Oh, thank you very much.
All set. So whenever you're ready, go ahead and
Okay, cool. Hello, everyone. So today I'm going to talk about the counterfeiting activities in the cyber supply chain and how do we use a nested game framework to characterize the counterfeiting activities in the cyber supply chain ecosystem. So with the development of the cyber technologies, many corporations have developed fast and convenient online markets and have moved their supply chain corporations to the cyberspace. So corporations like the Amazon, eBay, Walmart, they all have developed mature online markets and run their business by the cyber supply chain. So although the cyber business has merit of being convenience and efficiency, there are some security threats. One of them is the counterfeiting. So here are some data showing the severity of the counterfeiting in the cyber domain. So for example, according to the ICC report, more than 2 billion counterfeits were sold online in the United States in 2015. So therefore, the counterfeiting in the cyber market and the cyber supply chain are not negligible. Some special features of the cyber supply chains may exacerbate the counterfeiting threats compared with the normal supply chain. So we first give a short introduction to the supply chain and the counterfeits because we're discussing these two things, and then we'll go back to our topic. A supply chain is a network that integrates the business entity information resources to produce and distribute a specific product to the consumers. It contains many intermediate processes such as manufacturing, distributions. The licit supply chains, there are licit and illicit supply chains. So the following figure is a typical licit supply chains, and we will also see the illicit supply chains later. So as for counterfeit, when we discuss the counterfeit, we are interested in what characterizations of a counterfeit and how do they circulate in the supply chain. So the counterfeit can be characterized into or categorized into deceptive and non-deceptive counterfeit. The deceptive counterfeit can penetrate in the licit supply chain and circulate in that and cause implicit damage to the supply chain, while the non-deceptive counterfeits circulate through the illicit supply chain, causing the explicit damage. So the following figure gives an example of how deceptive and non-deceptive counterfeit drugs circulate in the licit and illicit supply chains. The drug here is an example. It can be any other counterfeits. This figure gives us an intuition of how the two types of counterfeits circulate in the licit and illicit supply chains. So back to our topic of the counterfeiting in cyber supply chains. What are the new features of the cyber supply chain? So the first is the structure of the cyber supply chain is more straightforward. So the postal service replaced the distribution process, and the retails take place online instead of the physical stores. So this makes it harder for the counterfeit inspections. So the second feature is the wide accessibility. Both licit and illicit market, the scale becomes non-negligible. So therefore, in this work, we will aggregate a lot of participants into a single player and focus on the population level strategies. And the third feature is clear, anonymity. The consumers have limited information about the product and the sellers. So this makes the consumers more price sensitive because the limited information that the consumer can know is the price. So these new features may worsen the counterfeit threats in the cyber supply chain because of lack of inspections and the real shopping experience. So based on these new features, the following models can be used to capture the interaction in the counterfeit activities. SI here represents the seller, and QI is the product volume. The licit seller, S1, it manufactures and sells the quantity Q1 to the licit market. The illicit seller, S2 and S3, they produce deceptive and non-deceptive counterfeit with quantity Q2 and Q3 and sell them to the licit market and illicit market respectively. Both will eventually circulate to the consumers. So by observing the market price, the consumers decides which market to go to maximize the utility. Okay, so our objective is threefold. First, we want to characterize and analyze the counterfeit activities in the cyber supply chain. Second, we focus on the interaction in the ecosystem of coexisting licit and illicit supply chains. Third, we want to investigate the anti-counterfeit strategies to mitigate the counterfeiting issues in the cyber supply chain ecosystem. Okay, so next comes to the models. Recall the model we discussed before. The competition between three sellers can be modeled as a non-cooperative game, and the intersection between the seller and the consumers, it can be modeled as a stackable game. So hence we have the nested game framework to capture the counterfeiting activities in the cyber supply chain. Now we introduce how to model the sellers and the consumers and then complete the formulation of the game. So recall one feature of the cyber supply chain is the accessibility. So the amount of consumers will be huge. Therefore, we assume that the market scale is 1. Each consumer is characterized by her theta, which is a random variable representing her interest in the real and fake product. So the consumers with small theta, they can tolerate counterfeits more. Theta equals 0 means that a consumer has the same interest in both real and fake product. She does not care about the product authenticity. So we assume that the consumer have the same valuation to the real product, but the valuation to the fake product is decreasing with theta, which is represented as phi g and phi f. The feasible action for each consumer is discrete, which is either going to the illicit market or going to the illicit market or buying nothing. Therefore, we can define the utility for different market choice. The U theta n means that the consumers buys nothing, so it is clear the utility is 0. And the rest of the utility is defined based on the following principle: the valuation minus the product, the market price. This U theta b is the utility for a consumer to go to the licit market, and this U theta o is the utility for a consumer to go to the licit market. Sorry, this is go to the illicit market. This is for the licit market. And then we can write in a compact form this U theta. So, sorry, I forget to introduce the eta. So when a consumer goes to the licit market, because of the counterfeit penetrations, we assume that some consumers in the licit market are vigilant and skeptical. So they prefer to think that the product is a counterfeit. So let eta be the proportion of the ordinary consumers, and 1 minus eta is the portion of vigilant consumers. And that's why this U theta O is the average utility. So each seller is also aggregated players. They decide how much to produce. The action set for each seller AI is defined as a unit interval. It is because the market scale is assumed to be 1. It is not necessary to produce more than 1 unit of product. So the seller indirectly make the price by producing the product. In the licit market, we assume that the price is linear in total amount of product, while in the illicit market, the pricing mechanism comprises 2 parts. So the first part explains the price taking strategy. The second term illustrates the price setting strategy. So this alpha reflects the compliance of the illicit seller with the legal market price. So we let DO and DB be the licit and illicit market share. The calculation of DO and DB will be discussed later. So we can define the utility. So the utility is the revenue minus the total production cost, which is direct and clear. So for example, for U3, we have this. But due to the counterfeit penetrations, the real market share for S1 and S2 is not DO. There is a fraction in front of it. Okay, now we are ready to define the game. So for the Stackable game, we have 3 sellers. 3 sellers are the leaders. The consumers are the followers. All the consumers maximize their utilities. So we denote the Stackleberg as GS in a compact form. And for the 3 sellers, we can define a Nash game, which is a non-cooperative game. Each seller wants to maximize their own profit, and the aggregated action space A is defined as a unit cube. We write GN as this Nash game. Okay, for the calculation of the market share, we need to be clear that the consumer provides the market share. By the Stackable game can be written as 1. So by solving the Stackable game, we can obtain the optimal strategies for the theta, and this theta will form the subintervals. The critical point at the boundary of these subintervals, the critical point here, the U theta ON, theta BN, and theta OB are the boundaries of these subintervals. So notice that the market scale is 1 from the assumptions. So the subinterval length can be interpreted as the corresponding market share. So for example, if I have an interval AB, and on this interval AB, I have U theta O is greater than the U theta B and the U theta N, which means, well, my licit market share will be the length of this interval AB, which is B minus A. Okay, so each subinterval length can be interpreted as the corresponding market share. There are a lot of cases to discuss to obtain the expressions of DO and DB, and this discussion will partition the aggregated action space into several subregions, as we will see later. Therefore, we can make some fair assumptions to simplify the discussion. So with these assumptions, we eventually obtain 3 cases, and in these 3 cases, we obtain a subregion. Inside each subregion, DO and DB has a unique expressions here. This is a sketch of the partition of the aggregated action space, and this is the expressions of the demand function of the market demand functions in each subregions. So as we can see that to solve the Nash game, it is ideal. The idea is to find the best response of each seller, and then we can use the fixed point iteration to find the intersection of the best response. But in the Nash game, as we can see here, the DO and the DB are piecewise linear function, which means that in the Nash game, the utility function will be a piecewise quadratic function. Therefore, we propose some algorithms to solve the Nash for the Nash equilibrium. For the time reason, I will introduce how to find the best response of R3. So the idea of the proposed algorithm is the following. We first note that the box constraint, which is a unit interval constraint, and the profit plane, as we see in this picture, the profit plane. There are two planes in the aggregated action space, which partition the entire unit cube. These two things are the main barrier to compute the best response. So first, we find the unconstrained maximizer of R3 in R1 and R2 union R3. And then we calculate the crossing point. And finally, we compare the objective values of at the unconstrained maximizers and the crossing point and the boundary point, and find the real response and find the real best response. So besides, we can actually obtain a nice best response of S3 from the following theorem. Basically, it tells the constraint for the best response of S3 to be a point-to-point mapping. Okay, so the idea of finding the best response of seller 1 and seller 2 are similar, but there are some differences. One of them is the fraction part. One of them is the fraction part in the utility function, as we saw in the previous definitions. So after finding the best response, we can use the iterative methods to find the Nash equilibrium as follows. So this iterative methods is the standard fixed point iterations. Basically, it tells first we calculate the best response of each players, and then we see that if this fixed point equation is satisfied, if it is satisfied for some epsilon, for some threshold, then we claim that we find the Nash equilibrium here. Okay. Before we move on, let's review a little bit. We have established a nested game framework to capture the counterfeiting activities in the cyber supply chain ecosystem. So in the ecosystem, we have licit seller, deceptive seller, who penetrate the illicit supply chain, and the non-deceptive seller who sell the non-deceptive counterfeits in the illicit supply chains. We can formulate a nested game to capture the interactions of the counterfeiting activities in the licit and illicit cyber supply chains. So next, we explore what factors will affect the market equilibrium, and the answer is the model parameters. So different from the traditional supply chain, the special features of the cyber supply chain are characterized by a series of parameters. The parameter sensitivity analysis will give us some idea of how the equilibrium changes in different situations, and how to design the effective anti-counterfeit strategies to mitigate the counterfeiting activities. So to have a more intuition understanding, we use a series of simulations to discuss and analyze the result. So as we can see, the first is the valuation elasticity. The consumer's tolerance on counterfeit is reflected by A. So as A is large, the fewer consumers are willing to tolerate the counterfeit, leading to a decreasing profit of the production size to the illicit sellers. We can let A equals 0.5, 0.3, and 0.33, leaving all other parameters unchanged. We can observe the market equilibrium at different A. So as A progresses, the counterfeit becomes less attractive because the production size of the counterfeit, as we can observe here, is decreasing as A increases. So the second is the weight of the price-taking strategy alpha. So large alpha means that the illicit seller is more willing to follow the licit market's sell price than setting the price by himself. So as plots indicate, so as large alpha corresponds to a small best response of the seller 3. The seller 3 sells the illicit counterfeit through the illicit supply chain. This means that the seller 3 gradually loses his price advantage as alpha increases. Therefore, we increase alpha, and the licit and illicit market will have the comparable sell price, and this will lead to the decreasing of the market of the illicit market share, as we can see from this from the figure. As alpha increases, the market share for the illicit market share DB decreases dramatically, and hence produce very effective anti-counterfeiting strategies. And the eta, one of the effect of increasing eta helps to reduce the size of region R1. So the smaller region R1 allows the S to establish a positive market share DO more easily. So as we can see, the total market share is fixed. So large eta, as eta increases, the size of the R1 decreases, which means the seller is more easily to grab more market shares, and hence suppress the behavior of the illicit sellers in the illicit seller S2 and S3. We run a lot of simulations, and we can observe that by increasing eta a little bit, the illicit market demand will decrease dramatically, and this shows the strength of the market belief. The last parameter sensitivity analysis is about the confiscation probability gamma. So S1's production size and profit are increasing with gamma, so as expected, because large gamma means that the illicit seller has more probability of being confiscated in the market. Therefore, gamma will have a positive impact to the illicit sellers. However, what I want to emphasize is that as S1 does not entirely absorb the market share freed by S2. As we can see this, as gamma increases, the risk of the illicit seller S2 be confiscated will increase. Therefore, the S2 will free some market share. But this market share is not absorbed by the illicit seller S1 completely. It is also partially absorbed by the illicit seller S3. This is what I want to emphasize. We can also see that from this simulation, the utility of S2 is negative when gamma equals 0.4. So this means that the confiscation risk is greater than the revenues of selling the deceptive counterfeit in the illicit market. And this provides effective anti-counterfeit strategies later. Okay, so based on this, based on the parameter sensitivity analysis, we have some insight of how to suppress the illicit sellers' profit and productions. So therefore, the following strategies can be used to mitigate the counterfeiting in the cyber supply chain ecosystem. So the strategies that improve the consumer's faith in the illicit market and reduce their tolerance on the counterfeit can weaken the counterfeit problems in the cyber supply chains. So based on the cyber platform actions such as the third-party cyber insurance for product and the digital authentication from the market organizer, this will help. So the second thing is the strategy that increase alpha can help diminish the counterfeit production size, because large alpha indicates the less power of the licit seller in setting the licit market sell price. And the next, improving the confiscation probability gamma can also suppress the deceptive counterfeits. Well, although it is potentially hard to trace the deceptive counterfeit in the cyber supply chain, the advanced technologies can be considered, such as using the QR code and the FRID chip for verification, and adopting the blockchain technologies to track the product life cycle. Okay, to summarize, in this work, we have investigated the equilibrium and the anti-counterfeit strategies on the counterfeiting activities in cyber supply chain ecosystem by establishing a nested game framework. We first analyze the feature of the cyber supply chain ecosystem and use a Nash game and a stackable game to capture the interactions of counterfeiting activities. They developed algorithms used to calculate the best response of the sellers, and the market equilibrium is corroborated by the simulations. Besides, the analysis for the analysis and the numerical experiment also proposed some effective anti-counterfeit strategies to mitigate the counterfeiting activities. And that's the end of the presentation. Thank you very much.
Great. So thank you very much for your presentation. And we have time for a couple of questions from the audience. So please raise your hand or post in the chat.
Hi, Johan. This is John Barras.
Hi.
You saw the very interesting discussion of the counterfeits and the networks and all that.
Oh, thank you.
But if I want to somehow defend it or and so on and so forth, I have two problems, right? One is, where do I detect the counterfeits, and then at what network is best to interfere with? So does your analysis tell me any? I know it doesn't tell me the first one, but does it tell me anything about the second?
I'm sorry.
Because you have several networks. You have a network to detect it. You have a network to send the information, and then you have the network of defenses and all that stuff. If I wanted to stop the counterfeits, where is most effective place to try to interrupt these chains?
Oh, I see. So I think the best the strategies that can stop the counterfeiting can be coming from these three ones. So basically, this work it captures and characterizes the interactions between illicit and licit supply chain ecosystems. So in these ecosystems, we have both the licit sellers and illicit sellers. They are interacting with each other.
But how do you know? Do you know them?
I'm sorry?
Do you know them?
Do you know them? This is a very good question. Actually, this is one of the potential future research directions, because basically here we just we assume that we model the competition between the licit seller and illicit seller as a Nash game. Because in the Nash game, in the non-cooperative game, we have the same informations. The information is symmetric, which means that we know each other. The players know each other's behavior and the actions. But in reality, yes, as you suggested, the information there should be some information asymmetry. So the illicit sellers may not have the licit sellers may not have the complete information about illicit sellers. This is a very interesting. This is a very interesting research directions. So for now, we have, I think, we have established the baseline, and then next time. And in the future research directions, we will definitely see how the information asymmetry will affect the behavior of.
And the other question, the other question I have is, many of these networks are international. In other words, what I mean by that is they cross boundaries. So a very interesting question is, to what extent can policies and agreements between nations and their financial consequences influence this problem? I mean, it's like, if you can think of it as an exogenous influence to a strategic game, right? Mathematically, I have an exogenous agent that comes in and puts some additional constraints on the game you formulated. Have you thought about that? Because that's an important question, because various nations try to collaborate in fight this. But I don't know if we understand well the economic and practical consequences of such policies and tariffs and agreements and so on and so forth. Any thought about that problem?
Oh, this is really a nice question. So actually, this is also really important in the counterfeiting activities. Well, actually, to be honest, well, from the engineering perspectives, I have to admit that this framework is inspired by the counterfeiting activities in the domesticated markets, such as the eBay or the Amazons, because we have witnessed the Amazon counterfeiting and the eBay counterfeiting phenomena very lot. But yes, I think, well, we need joint force from the maybe from the law.
Do you know if Amazon and all these online e-commerce companies, do they use blacklisting? Once they find some producer of counterfeits or some network, do they do blacklisting of that, or what do they do to avoid?
I'm not sure if they use the blacklisting, because actually I have 2 experience of purchasing counterfeit on Amazon.
Only 2. I have 5.
Oh, really? That's bad. They do nothing actually.
Yeah, right. It took me a while actually to figure out that I was a victim, but I finally figured it out because things were kind of strange, you know.
Oh, I see. But definitely setting up the blacklist is a very nice choice. I'm not sure if they do that, but this is definitely very constructive.
One possibility to look, I don't know if you care about these things, but there is, and I think Kwayan knows this, there is work, especially here in Maryland and other places, about the economics of security, okay? So, but I have not seen a good extension of the economics of these to counterfeiting and other stuff. In other words, to make the game a little bit more complicated, because now you introduce, in addition to the many things you described, which are all fine, economic considerations, you know, and things like that.
Thank you very much.
Yeah. And that'd be a nice, it would be very useful to know if there are strategies whereby the economics, agreements and tariffs and others can actually influence these markets. And but in reality, with real financial situations. Anyway, thank you again for a very nice presentation. I really enjoyed it.
Thank you very much for your question and suggestions. Thank you.
Thank you. So I actually have one more question for you. So I believe in your model that the sellers who are participating in the, so they were presenting counterfeit goods in the licit and illicit markets were separate players. And it seems like there's a lot of interesting potential strategies where, for example, a seller could try to flood a legitimate market with really low quality products in order to actually drive traffic to the legitimate market where they would stand to profit if they were the same player. So have you given any consideration to models where sellers could participate in both markets?
Let me go back to this plot. Okay, you mean this figure?
Yeah, so my understanding is that S2 and S3 are actually distinct players in this game.
Okay, yes, this is a good question. The consideration for the model is like this: S2 and S3 can actually be the same person in reality, right? But we can split that. Why? Because you can think in this way. If I am an illicit seller, I can both go to the illicit market and I can also sell. I can sell the deceptive counterfeits in the licit market as well as the illicit market. But selling these 2 markets is actually, I need to have a balance. That's why to have a balance, which means you need to make a choice. This like a competition, this like a decision, like a strategic competition between the two actions, whether to go to the whether to sell the deceptive counterfeit to the illicit market or sell the non-deceptive counterfeits to the illicit market. They can be the same person. But here, the first is that we are talking about the population level strategies. We aggregate a lot of participants into one player. So this S2 and S3 actually is not a single player. It represents a bunch of people, a bunch of participants. Therefore, if an illicit seller, of course, he can definitely reach to the licit and illicit market simultaneously. But under the population, but from the population level viewpoint, we just separate this person into 2 fake persons, and one can be represented by this illicit seller S2, and another is illicit seller S3. So this is the first from the population level perspective. The second is that, as I said, there should be a balance. If S2 and S3 is the same person, there should be a balance of choosing two different actions. And this actions is actually non-cooperative. If I go to the, if I am an illicit seller, I decide to go to the illicit market, well, it's definitely that I left less room for this illicit market. If I go to the illicit market, well, I will have less room for the illicit market. So the decision for these two actions, the decision for going to the illicit market and illicit market, they are in nature competitive. That's why we can split the same person into two fake persons and use different S2 and S3 to represent this. Yeah, I'm not sure if this is satisfactory.
I think that will do for now. So I think we're running a little bit over time. So
sorry.
So very interesting discussion, but thank you very much again for your talk.
Thank you very much.
So I think we're at the end of our session for today. So John,
thanks Chris. Yeah, thanks Chris, and thanks for the presenters. Very nice papers. We will convene again tomorrow morning at 10:30. I just want to remind everyone that we do have a very small group of people looking for candidates for the best paper award that we will give Friday. And I'm sure that you understand that your presentations as well, the papers are considered. So try to do your best when you're presenting. All right, the award will come with $500 honorarium. Okay, thank you again very much. And tomorrow we have actually an interesting also academic panel in addition to presentations. Thank you very much for participating, and see you tomorrow.